got a lot of chapters. I'm about 2 chapters behind, so I kind of want to get caught up. So here we go. Chapter 3. Chapter 3. Hopefully everybody had a nice week and we're up bright and early and you got your cup of coffee and you're ready to begin. Definitely need some kind of caffeine this morning. So, okay, so chapter 3. If you remember last Saturday, we talked about, well, systems administrator duties like chapter 1, and then chapter 2. I taught how the system boots up. Okay. You know, you have your little BIOS chip in there and it checks out the system. And then once it's finished checking out the system, it looks for a boot device. It looks for that master boot record. And then once that master boot record is found, it starts booting the system up. That master boot record is the initial boot, and then it goes to a secondary boot program like Grub. Okay. And then Grub will say, okay, I want you to go to the disk drive and boot this operating system up. So let's get started. Did I start the recording? Let's go see here. I did. Looky there. And so once the system then boots the OS up, it runs all those startup scripts in ETC and initd, but the startup scripts get started from the RC directory. So that's what we talked about last week. And if you missed last week, well, there's a recording up on YouTube that you can watch. Okay, so this chapter is about access control and rootly powers. You know, now, what does that mean, rootly powers? Well, in the Unix world, we call it being root, okay? And the root account means you have access to everything. And some of this is very similarly with Windows. You do have specific access control methods. For example, who has access to what? You know, what machines can they log into? Now, whether it's Windows or whether it is Unix, in Windows, what is the main account? I'm trying not to say it. What's the main account in Windows that gives us all of the privileges to do everything that we want to? What is that account called? Yeah, that's correct. Not admin, by the way. A lot of you are putting admin. It is actually administrator. Okay, administrator. And yeah, some people shorten it and say admin, but it's not admin. It's administrator. The account is actually listed as administrator. Likewise, over on the Unix side, it's called root, ROOT. Okay. But when we in Unix or Windows, we're always going to define access control and what you can and can't do. You know, who has access to what? Now, access means who has access to log into the machine. And even once they're logged in, what is their account type? Are they just allowed to access, you know, some minor files? In the Unix world, we have read, write, and execute. Okay, read, write, and execute. What programs can they run? In the Unix world, the programs, you can only run it if you have execute privileges. If you don't have execute privileges, you can't run it. Okay. So, and as far as accessing a file, you have to have read privileges. And of course, if it's a binary or an executable only, you know, it's right. I'm making the assumption that everybody knows when I say a binary file, okay, that people know what a binary file, but let me ask, okay, what's a binary file? Or actually answer yes or no, or not sure if you know what a binary file is. Do you know what a binary file is? Yes or no? It's definitely not 0 or 1, Shada. I mean, Okay, so I got a few no's out there. So in the world of Unix, you may often hear, and even in the world of um, of Windows as well, you may hear somebody say, oh, it's a binary file. A binary file just means that somebody wrote a program, usually in, say, C or C++, and they wrote that program and they then compiled the program. They used a compiler. And by using that compiler, they are actually taking what somebody wrote in some type of language, right? That they know what the language is. And then it is compiled into a binary program. In other words, ones and zeros, which is what kind of Shada said there, zeros and ones. But really, that's what they're referring to, is that it is a machine interpreted program that gives uh, that system the ability to run a program. So you can't cat it out and look at it. You can't more it out and look at it. If you were to try and do a dump of a binary file, you would see a bunch of gobbledygook. Okay. Give me a second here. Let me pull up my putty. So, basically, when we look at access control, the only way you're going to be able to write to a file is if it's depends upon the file type. So there are different file types when we get into Unix as well as even Windows. Okay. What directories can they access? Once again, we can give them read privileges or write privileges to access that directory. And, what type of actions are permissible? What are we going to allow that particular user access to? Give me 2 seconds. So if we look here, sorry about that. Trying to get this down. I used to be able to drag and drop pretty easy, but I loaded something. I'm not sure what. My windowing system fights with me these days. One of these days, I'm going to have to do a fresh install again. Okay, so here we go. We're logged into a Unix system. So binary, well, see that bin directory? That's really what bin comes from, okay? Binaries, files that have been compiled. And there's one of the commands we could run is file. Once again, if you don't know these commands, if you're going, oh, I've never seen that one before, then write it down in your handy dandy book where you, of course, are writing all of these little cool, make your own cheat sheet. I would have, if it was me and I was in your shoes, I would have my own little notebook for cool notes. And then I'd have another one where I would take, write long notes, a cheat sheet type book. But if I go file, okay, and let's type in cat. Look at this. See how it says it is a 64-bit shared object, dynamically linked. Okay, look at this. It's linked to a library. And then it says build. It gives us a build. This is a binary file. Okay. Let's see what happens when I cat it. And actually, let's do a different one. The bin directory, there's a lot of commands in here, folks. Look at all of them. Ooh, how about a copy command? If I go file, CP, it tells me it is a 64-bit LSB shared object. It's telling me basically that this is a compiled program. See where it says the build number? Well, now what happens if I do a cat of CP? Okay, well, that certainly doesn't look like, look at that. All that gobbledygook. Okay, that's because it's a compiled program. It's something that basically, the operating system, sometimes you can pick up some text in here. Look at this. You can pick up some text by catting it out, but it is a compiled program. Look, here's some more. So you can sometimes pick up some text from within it, but it is a compiled program. We can't edit it. Okay. So that's what binary is. It means it's been compiled. And the bin directory is basically where a lot of, that's what the bin stands for, binary. Okay. And that's where a lot of commands are, of course. So traditional Unix access control, we have objects, which are files and processes that have owners. And the owners have a broad control over their objects, meaning if you're the owner, you can do what you want with it. You own new objects that you create. So if you create an object, create a file, a directory, a process, okay, then basically you own it. You can do what you want with it. There's a special user account called root, and only root can basically access anything. If you're root, you can do whatever you want. And only root can perform certain sensitive operations. If we go back to PuTTY, and by the way, sometimes when you cat that file out, it won't let you type in legit commands. If we go to the ITSC directory, which we know that the ITSC directory is where a lot of the configurations for our Unix system are. If I do an ls minus al and I pipe it to more is going to page it, right? Notice all of these files, who are they owned by? They're owned by root. But when we look at this, this is the owner. First one's the owner. Matter of fact, if we go back here, let me go do it again, up arrow, okay? If we look at the root, this is the owner right here, okay? And this is a long listing of, an ls minus al. This is the command I like to do. I don't like to do LS's. Look at this. Because, yes, the color codes tell us, what they potentially are. But I don't like, I don't know. I don't like this. I like this. This is me, ls minus al. And I don't like colors. So a lot of times I'll do an unalias ls. And notice how my colors went away. Okay. But when you do a long listing with ls, okay, over to the left, you see permissions of whatever that is, whether it's a file, a link, a directory. And you'll notice over here, it gives the permissions. Notice that, and I'm going to go down here. See the D at the beginning? At the very beginning of this, it tells you what it is. If it's a minus symbol, well, that means it's a file. If it's a D, that's a directory. And an L would be a link. And so then it gives you permission. So read, write, execute. Well, that's for the owner. Whatever this owner is here has full read, write, execute to this directory called Apache 2, which is web server directory. And then the next one is group. And here you can see the group is R-X, meaning that if you're in the root group, meaning I could be J Wade and then be put into the root group, I would be able to read and execute that directory, meaning I could read what's in it, but I can't write. Notice the W is gone. And then the next one is the rest of the world. So everybody that has a login account to this machine can go to this directory and read it and take a look at it. Okay. And potentially execute something in it. If there's an executable in there, a compiled binary file as an example, well, then it could be executed. So, yep, if you notice right here, once again, owner and group. And then this is usually the size right here and the date of the last modification or change. And then, of course, the directory name. Now, notice this right here where it's got 8 and 3 and 6 and 1. What this means is that there's something called a hard link. A hard link, well, for all intents and purposes, when you look at that directory or file, if something's linked to it, okay, you really can't tell where it goes. A symbolic link will actually tell you, and let me show you. There's two types of links, a hard link. So if I go to ITSC, RC 3.D, this is a symbolic link. You'll notice that here in this, that it points to a name, and the name points to a script that's out there in init.d. The dot says go up one level and then into the init.d directory and find this load CPU FREQ. Once again, this tells when to start it up, and usually they're not all 0, 1, okay? It's an oddity, I think, of this operating system, which is GNU Linux. So that is called a symbolic link. It's like a pointer. But there's another thing that's called a hard link. Now, what is a hard link? Well, a hard link is something that we link, but it won't have, it will not have a, little arrow pointing to where it's going. It literally, and let's go do one. I'm going to go to my directory, and I'm going to create a file. I'm going to call it touch hello. That creates a empty file. And let's see, I've got a bin directory. Okay, hold on. Now, if I list it, you'll notice that, and I'm going to pipe it to grep hello. You'll notice there it is. See how it says 1 right here? Well, now watch what happens if I go bin. And I go link ... slash hello. Now watch. I'm in my own bin directory, okay? This is my bin directory. I created my own bin directory if I wanted to put, sometimes we'll do bin. There won't be binary, but we can put scripts in there for our own scripts. Notice, see how hello says 2 now? That's because the operating system is linking. They're the same file. If I go up one level, see how it says 2? Now watch this. If I remove hello, it's gone, right? I'm going to go to the bin directory and notice that it's back to 1 in the bin directory. So in reality, in the operating system, it doesn't copy this file multiple times. That's not what it's doing. It's hard linking to a single file. What the operating system does is it's keeping track of where you've done these hard links. Okay. So whenever you see that number increasing, that means that that is located in 6 different locations. Still just a single file. So what it's doing is it's a hard link, meaning the operating system is keeping track. A symbolic link is just that. It just is a pointer. So here we go. Here's a symbolic link. It's going to have a pointer that says, with the arrow that says, slash bin slash hello. Okay. That's a symbolic link. Lets us know exactly what it's pointing at. Okay. So here I have a hard link. And I can have slash bin slash hello. I can have slash etc slash hello. I can have slash, and give me 2 seconds here. Oops. Oops. Sorry about that. Hold on, folks. Okay. And then here I've got slash, let's say use, I still need to figure out how to disable the little buttons. Slash user slash bin. /hello. So here it would look like, oh, you've got this file in 3 different locations. Okay, 1, 2, 3, but it's all the same file. Okay, it is all the same file. Okay, so, and let's see, I got a question here. I am asked, so the inode is the same. Yes, the inode is the same, but the operating system is basically, you know, keeping track of the location. Okay. Now, some of y'all might go, well, what is an inode? Okay. Um, and basically, every object in the Unix has a unique identification number, an inode, okay, that basically, you know, keeps track, you know, or information about that file, whether it's a dev file or, you know, it's kind of like, you know, files, folders. Each one of them has a unique inode that the operating system keeps track of. We don't see it really from a perspective of, you know, the operating system, but that is what, let me go back. So hello has a unique inode. And when I do a hard link to it, like I did up here, the operating system is just keeping track of where that inode is located. And in this case, it was located in multiple locations. Okay. So when we go back to ITSC and you see all of this, you know, 3, that means that somewhere on the operating system, you've got 3 locations for those files. Hold on just a second. Okay. So every file that is created, as well as directory, has an owner and a group. And we just discussed that when you do an ls minus al, you'll notice here's the owner, in this case, Garth, and here's the group, staff. Now, these are names that we recognize, but in reality, these are associated with a UID, a user ID, and a group ID. We see basically what we've created. Now, let me ask this. Let's see who knows this. Where can I see Garth's? What file can I? Oh, well, I've got it right here. Never mind. Too early in the morning for me. I'm getting there, folks. Give me a chance. So Garth, as you can see, is going to have a user ID. And so it's going to be contained in etc password. And staff is going to have a group ID. Okay, let's go take a look. Just out of curiosity. Okay, it looks like I got 1, 2, 3, 4, 5, 6, 7 students logged in out of 19. For you 7, you get 50 points for being logged in. Okay, why log in? Well, because you can go and, you know, look at some of the same commands or do some of these commands that I'm showing you here. Look at it yourself. So, okay, so for all of y'all here, I got 1, 2, 3, 4, 5, 6, 7, 50 points this morning. Okay, for those of you that aren't logged in, I don't know, you know, me, I always like to log in when the instructor logged in so I could run the command myself, then take a little note in my book so I would remember it, so that I could learn and delve more into Unix. Okay. If we go to etc and we do a more of password, notice over here that here would be an example of your username at the very first. You'll notice here we got people's names. These are staff, like me. I've got Jay Wade. And here I have an X. That X, well, back in the day, the password file was the main password file, and you would see the encrypted password. But as technology improved, they realized, well, people can potentially decrypt that password. And so they hide it in what's called a shadow file. And we had our first script was that shadow file, which we can't look at here right now because it's protected, right? I mean, let's just take a quick look. Grep for shadow. You'll notice right here, the shadow file. Notice that, you know, the owner is root, the group is shadow, and the rest of the world can't see it. But up here, this is the username. It has a unique UID, and this is the UID. Okay? This 1937 is the UID, and notice this is the group ID. Now, in the real world, you won't see the UID and the group ID the same. They'll usually put that person in a group ID, like an administrator group ID or the web developer group ID, but you don't see it the same. This is what they're doing there. I don't know why they're doing it this way. It's not, you know, standardized or what the real world looks like. We don't give everybody their own group. It's just, you know, it's the way they decided to do it for since this is an academic. The next one is the GECOS field or GECOS field. And this field usually just has information. Like it might have, look up here. This one has Stuart Cook, which is one of the professors here. Okay. Here's Chris Button, another professor. And then you get the home directory. This is the student's home directory and where it's located at. Like this, home cook or home S cook, that's the professor's home directory, just like mine's home J Wade. And the next thing is, what shell is that person using? Notice all of this is separated by semicolons, excuse me, by colons, okay, by colons. So username, what, and this X just says refer to the shadow file. User ID, group ID, okay? And then here you have the GECOS field where we could put additional information. A home directory where that person, when you log in, that's usually where you go. Or if I hit CD, watch this, CD, enter, PWD, I'm in my home directory. And then, of course, the shell that you're using, which is the shell that it logs you in with. There are other items out here. Look at all of these. Some of these say no login. No login means that, well, there's going to be some process out there like UUCP or news that a process might be running, and we don't want anyone to be able to log in to that same that same username that the process is running under. Okay. So when you run a process, say you log in with your user account, I will log in with my user ID and I run a process. Well, the process runs as my user ID. I'm the only one that can kill it unless a root administrator, okay, that has a root account logs into the environment and kills my process. But other people can't kill my process unless they're in the group and I give them group privs. So when a program is run, the owner of the process is the user's UID and group ID. So as an example, if I run some kind of program, it runs as my user ID. And you can even see that if we go back here and we go PS minus EF, grep for J Wade, notice that these are processes. This column right here, this is the process ID, okay? And this is the process owner. See how I own these processes, meaning I can kill any of them. I can stop them instantly. And this is what's called the parent process ID. This is what called it. So take a look. I ran the command PS minus EF. That is a command that I ran. The owner, when I ran it, was me. And the process ID was 18248. But then look at this. There's a parent process, 17392. And if I look, I can see right here, 17392 is bash. When I log in, I get a bash shell. It is a process that will be running then. So there it is. There's my process that I am running. Likewise, it has a parent process ID, 17383. If I go look at 17383, you'll notice it is also bash. It has a parent process ID, 17382, which is, of course, SSH when I secure shell in. So here's what happens. I SSH into the system, and it executes bash and brings up the bash shell, which is a process. And even this one, look, 17361, it has a parent process ID. Okay. And then here, 660, if we wanted to, we could do a PS minus EF and grep for 660. So I'm just tracing those processes back. And look at this. All of us that have logged in, all of us, well, the SSHD daemon, the shell daemon, that's a program that runs. If that doesn't run, you can't log in with SSH. But all of us, when we log in, we end up connecting with this process that's listening on port 22. And then it takes us through that login process and connects us with bash and gives us this shell that you see right here that I'm typing on. Okay. So every process has a UID and GID associated. Remember that UID and GID? We don't see an ID. We see a name that came from the password file, or usually the group IDs come from the group file. This is the group file. You'll notice here, bin2. Look at this. Root is 0. It has a GID of 0. Okay. And then if we keep looking, here's all of these. By the way, this is more normal. See how all of these user IDs are associated with this group called ITSC 30020. And here is the group ID 1941. This is more normal that you see in the real world, where there's a group ID and the name. So this is the group name, the group ID associated with that name, 1941. And then you see a bunch of users that are associated with the group. That's normal. This is what we normally see. This is what you rarely see, or I've never seen until I came here, actually, is, where everybody gets their own group. Look at that. That's crazy. Okay. This is what you normally see. This is what you don't see in the real world. We don't give group IDs, unique group IDs to every person. You usually now, sometimes there'll be a generic group. As a matter of fact, let's see if it's there. Yeah. Staff is a lot of times what we put them in. We put everybody in the staff group. The other thing is you don't necessarily have to put them in the group file if in the password file you already have them in a group. So here, look, here's my group 1005. They're doing the same thing with the instructors, which, really, is not best practices. If you think about it, you would want the instructors all in the same group because maybe they want to share stuff on the UNIX system. And so they give certain privileges to a group, which would be called instructors. And then we would give it a GID. But anything that I run, whenever I type in any kind of command, it did a process ID instantly. See, look, here it is right here. J Wade, process ID. This here is the parent process ID, meaning the bash shell that called it. And here's the process ID, and there's my command, ps-ef. And if you look, I'm the owner of that process. Okay. Now, if we get a process that gets stuck, in other words, somebody wrote a program and it's in a constant loop, okay, then we would have to kill it. We can go do kill -9 and that process ID I showed you to basically terminate it. Okay, it'll get rid of it. So as an example, ps-ef, here's Joe. Joe owns this process, and Joe, of course, has a UID, could be 112. And then kill -9, 6244, the process ID, and it goes away. Now, here's the thing, folks. Here's the one thing on the Unix side you have to watch, and the Windows side as well. The Windows side also has, a similarly ID for everything on the environment. But here's what we have to watch. Let's say that there's a directory. Let's go to my directory. Here's my directory. And notice J. Wade owns all these files. Notice that the group is J. Wade, not normal. Okay, that's not real world. It's the way they do it. There wouldn't be a J. Wade group. It would be staff or instructor or something like that in the real world. But here it is, J. Wade. Now that J. Wade is associated with the password file. And there it is. There's my UID 1005, and there's my group ID 1005. Not real world, by the way, the groups. They're not doing them like the real world. So my question for you is, what do you think happens if in the password I delete my account? And I would delete it in the shadow as well. I delete J. Wade from password and shadow. And I delete the group out of the group file. Okay, if I grep for J. Wade from ITSC group, you'll notice there it is. Let's say I delete the password and my name out of the password and group. Question for you, yes or no, in the chat session. Do you think all of my stuff is gone? Yes or no? Awesome, great. Can access the system. Thanks, Lisa. And no, it's not gone. But let me ask you this. Is J. Wade going to be listed as the owner and group? What do you think? If I do an ls-al, am I still going to see my name there if I delete it out of the password, shadow, and group file? What do you think? What are we going to show for the group and the owner? What do you think? Anybody? Looks like we've got a lot of not sures here because nobody's answering. It will not still show it. And I'm going to give 50 points to Nicholas because you're the only person that got it. It will show just the UID. So remember my UID was what? 1005 up here. Let me go get it again just to make sure. One grep for J. Wade from password. Yeah, 1005. So what you would see here is 1005. And for the group, 1005. It would just have the UID and the GID. So the password file associates the UID and GIDs with names. Okay. And if it's a different type of group, inside the group, we might have a different group, like you saw that ITSC group. If you were to delete that group out of the group file, it would show a group ID, a GID. So if I go to and by the way, if I go to home J Wade, the J Wade would still exist, that name, okay, because that's not associated. It's basically somebody created a directory called J Wade. But if I went in and did a ls minus al of all the files, it would just show 1005 and 1005 right here. No, it would look something like this: drw x read dash x dash dash dash, and I'm going to say 1, and then it would show 1005 1005. Okay, that's what it would look like. So what does that tell you? That tells you that you've got to be careful when you remove somebody's account from a Unix system, because let's say that out here somewhere we have a directory called development, and this person is one of our developers, and he leaves the company, and we just rush right in and go, okay, let's remove that user from the system. And now all of a sudden we got these files out there that we have no idea who created them, because we can't see the username and group name that they originally belonged to. All we see, look, is these numbers. Okay, let's see. Oops, hold on. Oh, I guess I got rid of it. Darn it. So all we would see is those numbers. We wouldn't know who it belonged to. So what do we do? Well, usually when someone leaves the company, you have to search the Unix environments to see where their files might have left at, and then you have to change ownership of those files to somebody that's still with the company. Okay. Now, if they're not used or determined, yeah, we don't need those anymore, they might back them up to permanent backup and remove the files. Root account, also known as, you might hear it as super user. The actual username is root. It has a UID of 0. It allows any operation on any process, file, directory, anything. It has the ultimate power. Changing the root directory of a process with change root. We can create device files, set the system clock. We can raise resource usage and process priorities, set host names, network interfaces. Basically, can shut down the system. We can do everything when you are root. Now, sometimes we have a program, folks, that needs more privileges to run. In other words, if I go back, I might have a program that I wrote, J Wade. I wrote a script, or I wrote a program, and I need that program. Remember how I said that when I run something, I run it as myself. Right here. See, I did a PS minus EF, and I am the process owner. But here's the thing. What if I need to access files that are root as part of my program? Like I'm doing a backup or something like this. Well, there's something called set UID and set GID. It's a way to set the executable permissions on a file, allowing it to run as another UID or GID. It allows unprivileged users to perform privileged operation. Now, we don't like doing this as administrators. Here's the thing. Let's say that I have a shell script, a bash script, similar to the ones that we're writing. And I go in and I ask the administrator, I say, well, I'm having to do this and some changes. I need this process to run as root. So they're not going to go in there and do, change the owner to root, because you're the owner. What they're going to do is they're going to use set UID or GID and set the UID as root. And so now you run your script, and when it runs, it's running it as root. But here's the thing. You have to be careful, because a person could just put a break in there, a break inside the script, and break right into a root shell. That's what you have to watch out. Matter of fact, we used to use that as a kind of a way to get root access. So back in the day, when NFS, network file share, you could put on a file share, you could actually create a program that with a set UID where you had root access. So you go over to one server, you got root access, and you set a shell script with a break in it, and you set the UID to run as root. Then you share that on another system. You share the file system like a share drive, and you go over to the system where you don't have root, and you execute your little shell. That's how we used to bypass when somebody was administrating. We needed root, and they didn't want to give it. So there was always some little backdoor. Passwords, the ETC password holds the UID. I just showed you this. And shadow holds the encrypted password. Okay. Okay. Here are some of the distributions that we are working with or we discuss. Some of these aren't in your book. This slide is kind of from the previous book. Why do I leave this in there? Well, because you have other flavors of Unix. The book is titled Unix, but the author decided in version 5, I'm taking all the Unix stuff out. It's now really a Linux box. I mean, a book. I've thought about writing the author and say, hey, it's a Linux book now. It's not a Unix book. Ubuntu, an ideological community. SUSE. SUSE bought up Novell. Novell used to be an operating system in competition with Microsoft at one point to manage and create and manage, share drives and accounts and who could access what over a network. And then eventually they kind of got, we teach a whole class. Anybody had the Novell class? Anybody answer yes in the chat or no? Yeah, Lisa's had it. Yeah, we've talked a little bit, but we really haven't done anything that we need to take this class and really make it more of we can still leave Novell in it, but in reality, it's just another Unix class, with a little bit of Novell. And we've talked about taking that class and making it more Unix 3 with more advanced Unix, keep upping the course content instead of another Unix class. Red Hat, most companies use Red Hat. It has excellent support. And usually when you go into major companies, they're using Red Hat. Fedora Core is associated with Red Hat. They're community-based. CentOS is, it does a lot of compatibility with Red Hat. Solaris was from Sun Microsystems. Oracle bought them out, and it looks like, they may be, they're still out there, but you may not see as many as it used to be. HPUX is from Hewlett Packard, and AIX is IBM. And you still see some of the state organizations. Literally about 2 years ago, I was working for the state, and they had a ton of AIX. So modern access control has some shortcomings. First, root is a single point of failure, meaning that if somebody gets root account, good luck. Okay? A set UID has to be used to elevate privileges. And then the security model isn't that strong when it's used on a network. And they're talking about sharing stuff on a network. Okay. The other thing is multiple applications may have different access control rules. And it has minimal auditing support. So what does all that mean? Well, what if I want to give, you'll notice that when we, once again, let's go back to, if we look here, let's go to the bin directory. So I've got root as the owner and root as the group. Well, what if I want to give different privileges to different groups? Maybe I want to give, a group called backup and give them a little bit more access. What if I want to have different owners that can do different things? Like maybe I want one owner to only have, read and execute, and maybe another owner I want to have read and write, and another one I only want to have read. I don't want them to be able to execute it. So from a looking at this from a overall perspective, it has a lot of inability to do more granular control. It's too broad. It's, okay, here's the owner, give him full privilege to the file. I can only have one owner. Okay, here's the group. I can only have one group. And the rest is the rest of the world. What if I don't want the rest of the world to have access? I only want certain groups, and I want to be able to, have multiple groups, each with different privileges. So one of the things that they did was they looked at role-based access control, where they assigned specific roles. And to do this, well, they had to, give more granular access. Solaris, of course, uses groups, but they had this authorization right here and profiles that would create and allow you to create and assign different roles to different users. So I could have basically multiple groups, and depending on what group you are, well, you had certain access to certain abilities to do things. Okay, this was called role access. HPUIX would do the same thing. And so now we're getting into basically the other one was traditional access. Now we're getting into modern access. Okay, we have mandatory access control where all permissions are assigned by the administrators, but it supports the role-based access. But we wanted to come up still with more granular, so we came up with access control lists. Now, the first thing when you hear access control lists, you probably think, oh, routers, you mean? No. In the Unix world, we have access control lists, which accommodates permissions for multiple users and groups, and it's supported by different file system implementations. It was actually, look at this, actually based on Windows access control lists. This was NFS version 4, network file share. This is where we could share files across a network with a network share, but give different types of permissions to different users and different groups. One of the other things was pluggable authentication modules, where we had an authentication framework and a wrapper that had different authentication libraries. And what PAM is used for is it brings together an authentication library when people log in. So now we're getting more granular. We can get more granular with access control lists and list multiple owners and multiple groups that can do certain things with these files or directories, certain permissions. And then when it comes to authenticating or gaining access to the system, we can have programs that use these pluggable authentication modules to authenticate a person getting into the environment. One of the other ways that they made, or privileges was with Kirbos. Kirbos was an authentication method. Give me 2 seconds here. I'm trying to do something. And once again, my mouse is going crazy. There we go. Kirbos was a specific type. It still used PAM, but so you would have a application that could use PAM and Kirbos. What Kirbos did is it became a trusted third-party device that would provide credentials for the service. In other words, it gave permission, like SSH uses Kirbos. If I SSH to a system, well, that system would use Kirbos to give me some crypto credentials between the two end devices. Passwords. Root password and any password, the longer, better on passwords. When we log into a system, we want to look at the complexity. Now, back in my day, they didn't have, some of the Unix versions didn't have complexity. People could use whatever they wanted. I actually wrote a script. That script would try to decrypt people's passwords. And it wasn't so much the script as it was a script that used a program called Crypt that would try to unencrypt the password. And it was running 24/7 trying to unencrypt people's passwords. And if it detected something that was unencrypted, then it would immediately give that person 10 days to change their password. That was also done script. It would actually go into the shadow file. And one of the sections in the shadow file is how long the password is active. And what I'd do is I would change that date in there, which was a number, so that they had to change it within 10 days or it would expire. Then they had to call us to change it. You want to enforce, but nowadays, more Unix systems as well as Windows allow us to go in and set complexity. We can set the number of characters. We can set whether to use uppercase, lowercase, special characters, or numbers, and how many. Like you have to have a minimum of 2 uppercase, 2 lowercase, 1 number, 1 special character, as an example. We can require you to change it every 3 months, change it when somebody leaves, change when security is compromised. The other thing we haven't discussed is sudo. We're going to discuss that in a minute. One of the things they came up with a program, and that program allows us to give a user like me, Jay Wade, privileges on the machine as if I was running root, if I was root. And it can track it all. Now, there's a generic command called su, not the same as sudo. It is su. It means substitute user identity. This is where I, as an administrator, usually can log in and test somebody's account out. For example, Joe account. I could do su minus Joe account, and I would then be logged in as Joe. Now, notice the minus. There is a space between the two. The minus says to read the user's profile files. Remember, we discussed that last class. .bash rc or .bash minus profile gets executed when you log in. It's a way to set all your environmental variables, your path, your LD under library path. I discussed this the last class. And if you don't put the su minus, it won't source these, won't read them. It'll still log you in as the user, it just won't source. But we do this often. There's a couple of reasons we do this. One is we need to log in as a generic service account. Let's say we have a web server running and we want to log in as that web server account. So we would do su minus web account because that's what the Apache web server software is running as. And we would log in as that account using su. The other one is, well, maybe some user's having problems. Well, it doesn't work for me. I'm trying to do this. And you as the administrator, the root administrator. su is usually run by root, not by common users. Now, let's say you're a common user and you do su minus and the account. It's going to ask you for a password. Whereas when you are root administrator, you are, and by the way, I say administrator so you know when I say root, that means the admin account. So watch this. I'm going to do a su. And let's go grab an account from somewhere. Let's grep /etc/password. I'll just cat it out. More it out. Let me find an account here somewhere. Oh, there we go. Femi. So su minus Femi. And notice it asks me for a password. I would need to know that password and see, I just typed in something to get access to that account. Okay, but I couldn't get in. If I was root administrator, in other words, if I was root, I would do basically SU minus Femi, and it would go right in. Wouldn't ask me for a password because I'm administrator. Okay, that is the SU command. And once again, if you forget the minus, it doesn't read the bash profile files. Now there's another one. This one's called sudo. It allows us to delegate authority to users to run some other command as root, and it can also give us permission to run as root. The nice thing is it keeps a log file, so we know what the user ran, and a configuration file called the sudoers file. Okay, etc sudoers. And it could be in a different location as well. Depends on where you loaded it. But notice that here, I'm on an Ubuntu system. I type in sudo minus u operator, meaning I want to run the sbin dump command as operator. Now, here is the command. And what we're doing is we're dumping a disk. This is SDA1. But this is basically allowing me to run this as user operator. We mostly use this to run as root, so that I could do sudo user sbin dump and it would run it as root. This is where sometimes as well, you might say, hey, I need to run something as root. You know, you have a script, and that's where you have to be careful if you're allowing somebody to do elevated privileges. Not then, you know, and it's their script. Well, you have to watch out. Okay, let's go take a look. So each permission in the sudoers file, we can put a line as to exactly what they're allowed to run. Okay, we can also put what hosts they're allowed to. So we can centralize the sudoers config file so that it is shared across our infrastructure, giving permission only on certain servers. Let's take a look here. So here I have a sudoers example of a config file for sudoers. Here's host alias, CS. So I'm saying CS is equal to these hosts named Trigger, Anchor, Piper, Moet, and Siggy. And then I got another one called, and I guess that means computer science. And then I got another one called physics, maybe the physics department. ePrints, pPrints, and Icarus. Okay. And now I got a listing of commands. I have these command aliases. So dump includes sbin dump and sbin restore. Printing includes user sbin lpc and user bin lprm. And shells includes bin sh, tsh, bash, kshell, and bsh. So I have hosts defined, some host aliases with multiple hosts in it, and I have some command aliases with multiple commands in it. Now we get down to the permissions. Notice that two users called Mark and Ed are allowed basically to do all of these command aliases on all of the physics servers. Notice that Herb can basically, on the CS servers, can do user bin TCP dump. TCP dump is like Wireshark, where you listen on the network. And then on the physics computers, well, he can just do the dump command. So there's only two commands that Herb here can do. On the servers of the computer science department, on Trigger, Anchor, Piper, Moet, Siggy, he can do TCP dump. And on the physics server, ePrints, pPrints, and Icarus, he can do a dump. Okay, notice the dump means he can do sbin dump and sbin restore. Okay, and notice he's given the operator. He's going to do it as an operator. Linda here can do all, meaning both CS and physics, and all commands, dump, printing, but not shells. Now, that means that Linda won't be able to log into anything with sudo, at least. Really not going to be able to run very much because, can't do any shells. And then here's a wheel. This is just a background, or a process that's, part of the operating system. But configuring this file, you can see here, we can give people specific servers that they can run these commands on with elevated privileges that we've given them, and specific commands. And it also allows us to do logging. So sudo has some really good advantages. There's accountability because it does command logging whenever they do something. Operators can do chores without unlimited root privileges, meaning we can give them root privileges, but only on specific commands. You're only allowed to do this as root. The real root password can be known only to 1 or 2 people. In most cases, you may have only 1 or 2 people that know the root password, and then you give other folks sudo privileges. It's faster to use sudo than to use su or to log in as root. Privileges can be revoked without the need to change the root password. We just go in and edit the sudoers file, take away the privileges. The other nice thing is for auditing, when they want to audit, well, and by the way, I've had to go through this with companies auditing. They can literally come in and say, well, we want to know who has admin privileges. Okay, here's my sudoers file. There you go. These 2 administrators over here have the root password, but all of our other administrators, as well as all of our other staff, here is the sudoers file. All you got to do is take that apart. And when I say take it apart, I mean just read it. And you can figure out all the privileges that everybody in our environment has. There is a less chance of a root shell being left unattended, and a single file can be used to control access for an entire network. Yeah, that sudoers file, we can basically distribute it across the network, a single file. There are tricks you got to watch out for. Shell escapes. That's where somebody says, hey, I got a script, I need to run it as root. And you're like, okay, let me put it in the sudoers file. They then still have edit privileges of that script. And so they can go in and then put a shell escape. If they do that, also you have to watch out that those cases where, if we go back here, where we gave shell privileges right here, all these shell privileges. What that means is that anybody that has permission to do that can go sudo sh and they have a root shell. The other thing you have to watch out for is that you added the su command in there, meaning switch user. So they do sudo switch user and they can change to another user. And then false program, they configure something to run as a startup script as root. And when they do that, they have permissions to basically do anything. Now, one of the things that we do is we also store passwords in a vault. Sometimes they don't give root to anybody. You have to do sudo. And they'll basically take those passwords, they'll generate them automatically and store them in a password vault. Okay. And the other option of a password vault is the fact that, you can create more complicated passwords. And if you create those more complicated passwords, you can store them in a password vault because you can't remember them, right? Enables us to get more sophisticated passwords. Sudo users are accounts with special status, but they aren't allowed to log in. I actually showed you some of these sudo accounts, okay? They were the ones that said no login. Usually low UIDs, less than 100. /ETC shadow has a star for encrypted password, meaning that they don't have passwords. It's a star. And etc password to bin false or no login. It's needed for files and process ownership for the operating system, like bin, daemon, or nobody. So the operating system needs them. And I showed you this. If I go back and I say grep for no login from etc password, you'll notice, look at the user IDs. 1, 2, 3. Most of them are, all of them except for SSHD, okay, are lower than 100. And it looks like nobody's up there pretty high. But see, all of these are used by the operating system. And we don't want people to be able to log in, okay, with these processes. It's needed for the operating system to run certain processes and have those processes be owned by these accounts. But we don't want these accounts for someone to be able to log in and legitimately use them and get into the system. So that's why you'll see no login. Okay. Okay, that's it for privileges on Unix systems. Any questions? Answer no in the chat session or feel free to ask a question. Okay. Okay, folks, I've been talking for just a hair over an hour. It's 9:40. Let's take about a 5-minute bio break or get you some more coffee. It's 9:41. And let's say, I'm going to say 9:50. That's about a 9-minute break. 9:50. Yeah, let's resume at 9:50 a.m. It's about a 9 or 8-minute break. And I'm going to pause the recording. Please remember. Next chapter, chapter 4 is on controlling processes. So we brought all those processes up under our user ID. But there's still a few things. What if we want to kill it? And if you look at all of this, this is kind of funny. I must admit, whoever the author got to do this, I do like it. So you may want to kill a process. We can also prioritize how much CPU the process gets. Who gets more than the other? So when we look at processes, well, the operating system or the kernel uses internal data structures and records pieces of information for each process. Some of the more important is the process's address map space in memory, the current status, whether that process is sleeping, stopped, or runnable, the execution and priority of the process, meaning how much CPU does it get, and then there's information that it records about the resources that the process has used, like how much I/O or memory or CPU. There's also information about files and network ports the process has opened. And the process's signal mask. What is that? Well, each process can receive signals. The kill, as an example, is a signal that you can say, hey, kill the process. The command is called kill, and you tell it what signal you want to send to it. And then, of course, it records the group and the owner of the process. Every process that runs has a process ID, and the kernel assigns a unique ID to that process. Matter of fact, we just looked at the process ID a few minutes ago. If I do a PS minus EF, and let's go who. All right, let's see how many people I got now. 1, 2, 3, 4, 5, 6, 7 folks. And I got 20 people in class. That's disappointing. So all of you 7, I'm giving you 50 more points. If this is one of your UIDs here, you get 50 more points. And for those of you that are not logged in, you do not get 50 points. But if I do a PS minus EF, you'll notice at the top, here's the UID, the user ID that is running the process. Here's the process ID, the parent process ID. Okay. And then you look over here to the right, you see the different processes. See a lot of these with the K in them. These are kernel process. Okay, and then you can see start time. Here we go. You can keep on going down, get more information. The parent process ID, which we just saw, well, when a process is cloned, the original process is referred to as a parent. And the copy is called the child process. Okay. You have the UID and the effective UID. A process's UID is the user identification number of the person who created it. Or more accurately, it's a copy of the UID of the parent process. Usually only the creator and the super user can manipulate the process, meaning root can manipulate the process, kill it, as an example, or basically the owner of the process. The effective user ID is an extra UID that determines what resources and files the process or the permission has access to. By default, the effective user ID is going to be the same as the user ID. But remember that set GID and set UID process I talked about in that last chapter? Well, if you set the UID and GID to something else, that modifies the effective user ID. It allows us to take a process, and although that process may be owned by Jay Wade, it is effectively running as root because we did a set GID, set group ID, or set UID. So the GID is the group identification. The effective group ID is related to the GID. Once again, that's the set UID or set GID that we could set it. By default, the effective group ID is going to be the same as the group ID. Niceness. We can go in and change the niceness of a process that allows it and determines how much CPU time it gets. Okay, we can actually go set the nice value. Fork creates a copy of the original process. For example, the init process starts all of these scripts up. They become the child process. And we talked about this when the system boots up. Just a reminder, system boots up. Once again, the BIOS starts up the computer, does post checks, and then it looks for the master boot record on a bootable device. Then the master boot record says, okay, go get another bootloader like Grub. Grub then says, okay, let's go load the OS. Once the OS is loaded up and running, the init process kicks off and it runs all those startup scripts in RC1.d, 2.d, 3.d, runs all the startup processes. Okay. Those startup processes become child processes of the init process. The init would be the parent ID. Okay. Now, one of the downsides is if you have a child process that has a parent process and the parent process is killed, well, you may have, sometimes you have child processes you don't want running because the parent has been killed and can't tell the child to die. I know that all sounds funny, doesn't it? So we have signals, and every process has the ability to have some type of signal. Signals are process level interrupt requests. There's about 30 different kinds used in a variety of ways. They can be sent to the processes as a means of communication with the process. As an example, they can be sent by the terminal driver to kill, interrupt, or suspend processes when keys such as Control-C and Control-Z are typed. They can be sent by the admin, like with a kill command. And they can be sent by the kernel itself. The operating system can send a signal to that process. And they can be sent by the kernel to notify a process of some bad condition as well, like the death of a child, process. Here's some of the signals. Hup, meaning hang up. Int, interrupt. And so you can do this command as an example, the kill command, and we can go kill -3 and the process ID. That would be telling the process we want to gracefully quit. -9 here literally kills the process. Kills the command, -9 process ID. It just terminates it. Okay? It just terminates it. Segmentation fault. This is what you usually say the kernel sends that a lot of times. Kernel sends that one. And the kernel also sends this one. Usually when something's wrong, the kernel will use this. And then you can see some others down here, user defined. When you do a hup here, a lot of times this hup, it doesn't kill the process. It tells the process to reread the config file and restart. A kill -hup, like for send mail, would tell it to reread the config file and restart send mail. Okay. If you run kill -3 on a Java program, it won't kill the Java program. It'll do a Java dump. So it dumps memory of that Java process. So some of these do different things. Of course, -9 just flat out kills it. Sometimes -3 tells it to quit, gracefully shut down. So kill is unblockable and terminates a process at the kernel level. That's the one I was just talking about, kill -9. Init, so we're just looking at some of the best known of these. We're going through these, okay? Oh, by the way, you can use the word or the number. So I could have said kill hup PID. So the kill, which is -9, it just says, you know, see, it says a process can never receive a signal. It just says, tells the kernel to terminate it. Stop it immediately. Init is sent by a terminal driver when we do Control-C. It's a request to terminate the current operation. So in other words, you run a process or a program in the window and you don't get the prompt back. It's just running away. And you can Control-C it and it will interrupt it. Programs that have an interactive command line, such as this shell, should stop what they're doing, clean up, and wait for user input. It's a way to kill something. You're running it in a window. So if I run something here, let's say I run the PS -EF and it gets in some weird loop and just keeps on going. Well, I can do a Control-C to get out of it. That's how we get out of stuff that we're running. Or I run a script, and that script is in a perpetual loop. I could basically then get out of it. Ooh, we could do that. Let's see. I'm behind, so term is a request to terminate it. Hup. So hup has two common interpretations. First, it's understood as a reset by many daemons. The daemon is capable of rereading its config file and adjusting changes without restarting, while a hup can generally be used to trigger the behavior. Sometimes it allows you to basically clean up the process, okay, and basically hang up. So it does sometimes. A hup means terminate it. Sometimes depends on the program. So how do we send those signals? Well, with the kill command. Kill -9 tells the kernel to terminate it. We can also do another command called kill all and tell it, like HTTPD. What it'll do is it'll kill all HTTPD processes. And then we could do a pkill -u bin to say, hey, I want you to kill any processes that bin is running. We would have to be root to do this, or have sudo that would grant us root privileges to run that command. When a process runs, it can be in 4 different states. Runnable, meaning it's actually being run and executing the program. Sleeping, meaning it's waiting for some resource like I/O. An example would be a database program reading something from the database, and it's waiting for it to finish that read. Zombie, the process is trying to die, but it's stuck. Okay. Stop, the process is suspended, but it's not allowed to execute. Nice. Nice is where we set a value to give it higher priority on the particular program, or lower priority. So as an example, nice minus N5 lowers a priority, okay? Lowers the priority, okay, by 5. Or we could raise it. Re-nice minus 5 sets the nice value to -5. And re-nice 5 for user bog sets the nice value of bog processes to 5. So I could do all the user's processes, I could do a specific process, or I could lower it. So I could lower it or raise it, or I could just set it. These two are setting it. These two are, this one is lowering or raising it. Here are the different priority values for nice and re-nice across the different operating systems. So Linux is from -20 to 19. Obviously, the lower the value, the lower the priority. Solaris 0 to 39, HPUIX 0 to 39, AIX -20 to 19. I don't know why these two decided to use negative numbers. I wonder who decided that. I would much rather just use, hey, set it to some positive values. But I guess somebody said, well, no, we want it to know it's really low. So I don't know. So how many priorities are there? Well, here they are right here, Seth. Here's the priorities. -20 to 19. So what is that? 40? About 40 values, I guess. So 39, but then you have to add the 0. So, okay. Now, the PS command that I've been doing today gives us a lot of information about the process. We use that command to see what processes are running, but there are different types of commands that we can type in. Look at this, PS minus AUX output. So just like all of our commands, they all have different variables that we can add to it, different attributes that we can add to the command to get additional information. So here we can get the username of the process owner, process ID, the amount of CPU the process is using, and the amount of memory. The virtual size of the process, meaning how much, virtual memory is it taking up. The resident set size, this is actually the physical amount of memory in pages that it is using. So when we look at a program to see how much memory it's taking up, we look at both the virtual size and the resident set size. Control terminal ID, the current status. For example, is it runnable, sleeping, a zombie, or is it in an uninterruptible state or a traced or stopped state? Here's some additional flags. The process is swapping out. The process is higher than normal priority. The process has lower than normal priority. And some pages are locked in core. And then, of course, you have the CPU time that the process has consumed, and, of course, the command itself. Here we go. If we run PS minus UIX, here we go. Here's the user that owns it. Here's the process ID. Here's the amount of CPU, the amount of memory, the virtual set size, not very big, right? The resident set size, physical memory, the status. And I can't remember all of these myself. I know some of them, like R for runnable, S for sleeping, and Z, but when it gets to D and T and all of these additional flags, I don't have those memorized. Really, when we look at something like this, we're really looking at these 4 columns right here. The CPU and the memory. We're looking usually for processes that are maxing out the memory or maxing out CPU. Or we're looking at these virtual or resident set size to see how much they are. Another one we can do, a couple more attributes, is PS minus EF. Notice the output is slightly different. You have the user ID, the process ID, parent process ID, the CPU use, okay? And by the way, this isn't percentage of CPU usage, because look, 203, it's really from a perspective, you're looking at who's using the most CPU time. In this case, it is Trent over here at 203. And then you have the time the process was started. You have the control terminal, the CPU time consumed. We also look at this. So here the init process is used the most. Well, it's running all those scripts. And then the command and the arguments. Notice EF, I could do a ELF output. Each one of them gives me a little bit of different information. So here I've got F for process flags. I have the process status right here. So these are sleeping, and this one's stopped. We're doing a trace back. I have the process ID, the parent process ID, the process CPU utilization scheduling information. So again, it's different, slightly different format. P, scheduling priority. The nice value right here. Here's 20 and 20. That's the highest value, right? Because it went from, no, I wonder what, oh, this is HPUIX. That's why. It goes like to 0 to 39. So it's not the highest. And then at memory address of the process, where in memory that process is running, the size and pages of the main memory, and then this address of the process is waiting for, and then, of course, the command itself. So notice it says PS and top. Well, what is top? Well, and by the way, you won't find this on all flavors of Unix, but let's take a look. So PS minus AUX. Notice that the format is different. If we go all the way to the top, it tells us here's the amount of CPU and memory right here. And then look here, this, we look down and we look to see, okay, is there any large resident set size, any CPU? You can also do some sorts by CPU as well. Then we had the PS minus EFL. Here we go. Once again, slightly different format. Priority, it shows me the priority. Shows me the nice value. Shows me the command. But another one that we use quite often in the administration world is called top, T-O-P. Top just constantly runs all the time until you, watch this, Control C. See, I did a Control C, it interrupted me out. Just like we saw a minute ago, and we'd said, if you're running some type of program in it to get out of it, you can do a Control C. But look at all the information I get up here. It tells me 187 tasks are running, or processes. One's running, 185 are sleeping, and one is stopped. No zombies. It tells me the amount of user CPU, meaning you, the user, system, meaning the operating system, how much CPU it is, the nice value, and look at this, 98% idle. So we're currently 98% idle. So when we're using top, here's what we look at, folks. We look to see what the CPU is and the idle time. If that idle time is like 2%, that means we're 98% of CPUs being used. We also look to see what's using it. Is the operating system, or is it users like me? And over here, look at this. See this wait time? This is how long we're waiting on I/O. A lot of times we can tell it on wait time if there's a slow disk drive, or if the system is swapping constantly to disk. Well, we can tell by the wait time, it will increase. Wait time means the CPU is waiting for I/O. We don't want high wait times. I've seen wait times get up to like 80, 90%, meaning the system's just sitting there waiting for I/O, usually caused by a bad disk drive. Okay. So really we look at the wait time, we look at the idle time, CPU time, user time, and then we also look, if you look down here, see how it tells me the amount of memory we have. So it looks like 8 gigs. Looks like this is how much free that we have, and this is how much is being used. Now, this might look strange because you might say, well, wait, if there's 8 gig and we only have a gig free, but we're only using 3, so that's what, 3, 4, where's the other 4 gig, Professor Wade? We'll see where it says buffer right here. Look at that buffer time. And that's not 1 gig. That's actually less than 1 gig. Okay. That's like 100 meg free. See the buffer here is 7 gigs. 7 gigs. What a Unix system will do is, and notice it says it's dividing it into buffer and cache. What a Unix system will do is it will use any available physical memory for a disk cache. Okay. In other words, it'll use that memory to increase I/O performance by caching or having a buffer there for I/O going to a disk drive. If a program comes in and needs the memory, it gets it from this cache. So some people look and they'll go, oh, wow, we've only got like 137 megs here. Man, that's not much. We need more memory. But what you need to look at is this. This says that, no, you've got 7.7 gig being used by buffer cache, meaning it's doing disk caching. And by the way, I want to make sure everybody understands. Does everybody understand when I say disk cache? Yes or no? Disk cache. Do you understand that? Yes or no? Because I'll explain it if somebody says no. Or if you're not sure, that's fine. Don't be afraid to ask. Okay. So I've got a no. So let me explain what disk cache is, folks. Let's go back over here. So here I have a computer. And we're going to say this is a Linux computer. And here I have a disk drive. That disk drive's inside the computer, okay? Inside the computer. And here I have CPU. Here I have memory. Physical memory. And we'll say this is 8 gigs. And I got 4 cores. And I got a 250 gig disk. Yeah, we're going to make it a small disk. And that's inside the computer. Now, let me ask you this. What do you think is, and I have, here we go. I got all this program running, bunch of programs running. What do you think the slowest part when we run a program on our computer and we talk about the data flowing? What do you think the slowest area it flows? Do you think it is CPU? Do you think it's memory? Or do you think it is disk? What do you think? Yeah, it's disk. It doesn't matter whether that disk is SSD or HDD. In other words, whether it's a spindle disk or whether it is an SSD, it's still slow. It has to cross a bus. The CPU and memory, if we look at a motherboard, what? You got a CPU in here and you got the memory chips right next to it. What does a disk drive do? Whether it's SD, well, there's a bus in there. There's the bus. The bus is connected up to the disk drive. This is slow. Doesn't matter whether it's an SSD or an HDD. Yes, it's faster with an SSD. Yes, a lot faster. But it's still slow when compared to this program running and you're accessing memory. So there's a process called caching. There's a lot of things that use caching. Web server caching, okay? Web requests cached. Databases cached. What it is they realize that memory is faster. This physical memory is faster. So here's what it does. It takes this physical memory, and so here we go. Here's memory. And I might use this amount of memory for my programs. And then I've got all of this memory here, like this might be 2 gigs, and this is 6 gigs. And 6 gigs is just sitting there doing nothing. It's just sitting there doing absolutely, utterly nothing. But we don't want that. We want it so, we might as well take some advantage. So here's what we do. We create a cache, meaning a storage place, so that as we get data from a slow device, like our disk drive over here, we can put it into memory. We can buffer it up and put it into that there first. Memory's faster. So imagine I have a program, and the program needs to go access the disk drive. Well, do I want the program to do this kind of stuff, just back and forth to the disk? Or, here's the program. How about the program accesses memory, which is a lot faster, and then memory accesses the disk and buffers it up very fast, okay? It just starts grabbing all that data, kind of streaming the data into memory so the program can operate on it in memory. It's called a disk cache. It's a way to speed up disk requests, because really the program, the operating system itself, not just the program, the operating system is accessing the memory, and you've buffered up portions of that disk data into memory. Okay? Everybody understand what a disk cache is? Any questions? That is what a disk cache is. You're using memory, okay, so that you can buffer and speed up the request going to the slow I/O. I still got no's. Okay. Give me 2 seconds here. Oh, no questions. Okay. Okay. So that's what a disk cache is. Okay. So when we go back and look at that top again, what you're seeing here for that 7 gigs is disk cache. The operating system is basically buffering those I/O requests into memory to make it faster going to the disk drive. Matter of fact, did y'all know that most disk drives, HDD drives, actually have a little bit of memory on there to buffer requests to speed up that access? They do. Look at the specs on a hard drive and it'll say buffer, the amount of buffer. But what if we are loading a new program and we need more than 138 megabytes of memory? Well, it'll steal instantly from the cache. It'll go, oop, I need 2 gig. Give it back to me. I got to run some programs. Got to load programs into memory. So buffer, I'm reducing you down. The other thing that we look at in top is this, swap. Now, what is swap? Well, memory on a system, whether Windows or Linux, is virtual memory. It comprises both physical memory, those chips, and disk memory, where we took disk and we said, oh, we need a little bit more because we fill up with physical. What that means is if you have some huge giant program or a bunch of programs and you fill up your physical memory with all of that code running on the computer, it's going to use the disk drive to go out there and basically use that as memory. It's usually a partition. We can take an entire partition or a file on the disk. What you look for, though, let me ask you this. Let's say I use up all my memory, but I've got, look at this, it's got 8 gigs of swap. So, 16 gigs of memory on this, 8 gig of physical, 8 gig of swap. Notice it says 0 used swap. Let's say that this said 6 gig of used swap. Do you think going out and using that physical disk as part of my memory is going to slow the system down or speed it up? What do you think? Slow or make it faster? Yeah, it's going to make it slower. It's going to make it slower. As a matter of fact, what's going to happen is whenever you see this swap going up, these wait times over here are going to go up because it's going to be waiting on I/O. Doesn't matter if it's an SSD drive or HDD. The SSD is not going to be as bad, right? But it still has to go through, as I drew that diagram, a bus to get to it. It's not directly connected memory. So those are some of the things that we look at. We look at, once again, this CPU percentage right here. What's the idle time as an example? And is the operating system or the user taking it up? We look at the wait time to see at what are we, if we're waiting on I/O. We look at the amount of memory, and then we also look at the buffer to see if it's being used. Now, when you worry about physical memory is when this buffer gets down to 0 and you see the used here go up to 8 gigs, and then all of a sudden you see the swapping being used as well. That's when you go, oop, we need more physical memory. Next down here is the regular PS information, but it's constantly updating until I do Control-C. We look at CPU and memory percentage. The other thing we have the ability to do is sort by these columns. You can do like, say, M to sort by memory, and we can sort by CPU. So you notice you can sort by CPU and memory and some of these other columns, like the virtual size over here. So we have the ability to basically sort by the columns as well, which is really nice. Okay, well, that's TOP. TOP is a big time diagnostic tool. But where does it get all of this information from? Well, there is a file system on here called /proc. And if I change directory to /proc, you see all of these directories out here. And you also see these numbers. Folks, these are process IDs. And in these directories, we can go and take a look. Let's see, let's go. Let's grep for me. Actually, let's go. There we go. I got some directories out there. Pretty cool, right? But let's go look for a process ID. Grep for J Wade. Let's go look for, no, those will be gone. Let's look for 17382. See if it's in there. 17382. And there it is. I just listed it. I could change directory to 17382. You see all of these files. See, I am in my own process directory that the kernel is using this to keep track of items. Let's see if there's anything. How about we go cat stat? See the information in there? Some status information. I can't read this. Sometimes you can read exactly what's in here. But when you run the PS, it's getting it from that information from here. And there's more than just process information in here. Notice, look at this. Swap information, stat information, uptime information. Watch this. Cat uptime. Ooh, I can't read that. Well, when you type uptime, where do you think it's getting it from? It's getting it. It's getting this information from here. Some files you can't read, some you can. We don't really go through here and cat all this because there's an associated command that all this is for the kernel to store information. Okay. So process information in that /proc directory, you have different subdirectories as well, in addition to the process ID. Command is command or programs the process is executing. Command line is complete command line of the process. Environment, I'm not going to go over every one of them, but exe, symbolic link to the file being executed. Stat is general process information, best decoded with PS. He says best decoded. Root, symbolic link to the root directory set with change root. Stat M, memory usage information. Oh, let's go look at that. Let's see. Let's go. I'm using up arrow. There we go. To get back to my directory. I didn't remember what it was. Let's see. Stat M. Let's go cat stat M. There we go. It tells me a whole lot of information. Okay. That, you know, the kernel knows that information to basically do my memory usage. Okay. Now, you can also use some other commands for on AIX and Solaris. AIX and Solaris has that format you if you were to go to the proc directory on AIX and Solaris, same thing. You can't interpret it. It may be just a bunch of numbers. But you can use pcred, which is going to print and set real effective and saved UIDs. You can show library dependencies. You can list signal actions. You can print open files. You can print the current working directory. And you can, you know, so there's some commands that you can execute against a process ID to get additional information specific to the process ID. One of the other things we can do with a process is we can run strace or trust. This is the way to actually trace the process. Let's go see. By the way, I've found memory leaks with this before, but I use trust. That is on Solaris. Let's see if this version has trust. I don't think it does. Nope. Let's try strace, and let's go. Oh, it doesn't have it on there. It looks like this version doesn't have the commands. So let's see. How about sbin? Nope. Okay. So we can use strace, trust, and TUSC. So here, look, I'm running strace minus P on a process, and it's basically doing a trace. It's going into the process and doing a trace to see what the process is doing. We often utilize this, or developers do, to debug a process that may be having problems. So for example here, if you kind of look down through this to see what it's doing, and this one doesn't show us much. Let's do a different one. Take a look at this, Solaris Trust. And I've used this before. Notice that we did a date. So here, what this is doing is it's saying execute the date command, but I want you to trace it or do a trace as you execute it. So it's actually tracing the calls that binary program is executing. In this case, it's accessing zone info. This is a library file, so it accesses this Mountain Standard Time library file. Then here it writes the date. So you can actually see where, oh, it's doing mountain time, Mountain Standard Time. It's reading the time zone, and here it's writing the date. And then it's exiting. So it's basically, this is doing like a stack trace of the actual program. Developers use this to help debug their programs. If it's having problems, they can run a truss, doing a stack trace of what that binary compiled program is doing. This is more for C++, you know, or, you know, when you've compiled a C program. You can also have a runaway process. This is where some process is running. How do we find it? Well, top is what I use. We go and look, and when we run top, what we're looking for, obviously, running top. Here we go, top. We run top. We're looking for something that has a process that has a ton of CPU and memory, either or, okay? Or even disk. You might see some IO wait just going through. There's other commands we can look for that. But what you're doing is you're looking for any user processes that are consuming excessive resources, or even sometimes a system process, a bug in it that's having some kind of wild behavior, grabbing up all the CPU, or maybe has a memory leak. Memory leak means that the memory isn't being released by that process, and it just keeps consuming more and more memory. We use programs like PS or top, uptime to show load averages. Let's execute some of these, folks. Once again, these are commands you should know. If I was hiring you for a Unix job and you didn't know these commands, I move on to the next person. So PS minus EF gives us information. Remember, we have different parameters. I can do a PS minus EFL, and it shows me, basically, if I go all the way to the top, hold on, it shows me the, process ID, the priority, and it shows me what it's nice. Let's do the other one, PS minus AUX, and this one is going to show me, if I don't go too far, it's going to show me the CPU and memory. So PS minus AUX. But I really don't use these as much, I will admit. What I do is I run top. It's the first program that most administrators go to because it sorts it. I can use hit like an M for memory, and then it'll sort by the memory column or the CPU column, and I can look and see what's grabbing CPU or memory. I can also look at my overall resources up here as we've gone through. Another command we look at is uptime, okay? We look at these load averages. This is the load average of the system. The higher the load average, well, the worse it is. Also tells us the number of users. I got 12 users. Let's see. There we go. Looks like I got a few more logged in. Awesome. If you've logged in, and anybody else that's logged in, if you've been logged in the whole time, here's another 50 points. And for those of you that haven't logged into the putty session, and I'm sorry you don't get 50 points. You go home at the end of the day feeling horrible, okay? And of course, if you've answered any questions, 10 points, okay? Whether right or wrong, 20 points if you were right. Even if you just answered yes or no to me, you get 10 points. You can add these points up at the end and go away. Yeah, I got 150, I got 200, I got 230. Or you can say, oh, I didn't get any, you know. Okay, now notice down below, we're going to go over these commands. DF minus K. Let's try it. Okay. Well, this gives us disk space. Now notice we got this temp file system right there. Now, this is a weird operating system. If you just do, I've never seen where the temp FS is like this. This is really weird. Probably because if you do a DF minus H, and I'm going to do a grep minus V says, I don't want to see temp FS. Okay, it's a temp file system, but I've never seen it broken down by users like this. This is GNU's Linux, and I'm a Red Hat person, okay, as are most corporate people. So here we go. Notice I did DF minus H. This says, and this is why I like it, because see, look at this. I have a root system where we have 5.6 gig used, 21 gig of available. And the total size is 28 gigs. Here I have a home partition, 81 gig used, 72 gigs available. This is what we would use to see, oh, do we have disk space filling up and which partition? Okay. And if we do the df minus k, and let's do a grep minus v, get rid of that temp fs. Notice it's in kilobytes. And I don't like kilobytes. I'm like, show me the amount of gig or meg. I like it that it puts it in meg or gig. So that's df minus h. By the way, that minus h minus k, it's different sometimes with different flavors of Unix. Okay. Now, once again, don't forget the man pages. If you want to see more, well, there you go. Minus A includes pseudo, duplicate, inaccessible file systems. Minus H, human readable. Okay. Print sizes and powers of 1024. Minus K, block size in kilobytes. Okay. List inode information. So all of this is a different, remember, for every command, you can go and look to see if there's additional information. Now, DU, what is DU? Well, DU allows us, let's go do a DU, meaning estimate file space usage. It's a way to tell me how much space I'm using. So let's go to /home and let's do a DU, and I'm going to do of J Wade. Let's see what it says. Ooh. Well, it went down in there and it showed me the file sizes of my entire directory. You see all of this right over here? This is the file size. But here's what I want. I want to do a DU minus S of J Wade. Now it just shows me a summary of what and the size of my directory is. Okay, once again, 1, 2, 3, 1, 2, about 1.3 gigs. Okay, how about DU minus, let's see if the H works here. And it does, 1.3 gigs. So I'm taking up 1.3 gigs. Now, if I wanted to go in and see where that was at, I could go JW Wade. I could go DU minus SH a star, like everything. And notice it lists all of the directories. This is how we go in when, to figure out, well, where's all the space? Where am I taking up? The administrator says, hey, you got too much disk space. You need to reduce it down. By the way, we can actually go in and look here. I've got my backup tar right here. Okay. So let's get rid of that. By the way, that tar is there from one of our labs. One of our labs, we're going to look at the tar and do a tar command. Okay, so that got rid of some. Is there any more here? K, K, K. You know what? I'm going to go up and do this command again, but I'm going to do grep minus V of K. Let's just see the megabytes. Okay. It didn't work very well. Did I do a low? Oh, I did a lowercase k. Okay. Meg. So this would be the next biggest one, tars. Let's see what's in there. This is how we clean up something. Okay, I have a bunch of tars in here. I'm going to remove all of these. Actually, let's go up. We'll just remove the whole directory. RM minus R of tars. Minus R says do a recursive. By the way, if you haven't seen these commands, don't just look at them. Write them down. Okay? All this stuff I'm showing you, I'm telling you what commands I'm using so that you can go and say, ooh, okay, so if I want to remove an entire directory, the minus R for recursive. And there we go. It's gone. Entire directory. Okay. So that was DU. The other one is LSOF. LSOF. This finds open files on a per process basis. Okay. If I just do an LSOF, see, it prints a bunch of stuff. Some of it is not going to let me, do it, but I could print a particular process that I'm running. Let's see. Let's go do a man of LSOF. list open files. Now, why do we do this one? One of the reasons that we do list open files is sometimes a program can go grab a really giant file and pull it into memory. And so what we're doing is looking to see if that program has some giant file opened up and it's basically loaded it into memory. Okay. So anyways, that's LSOF. And if we look at the output here, and it's kind of hard to see it just because, let me extend that, do an LSOF. And see, notice it lists right here. These are file sizes right here. So see how it's got some library opened up. And see how it, when you do an LSOF, it tries to do all the processes. And see, I'm getting all these permission denied. My processes, though, it is going to list some of them. Some of them it is going to list. You can see it is listing. And here's some of the files, all these library files that it's opened up to run. And here's the size. Okay. And then here's a bunch more permission denied. So when you do an LSOF by default, it's going to try to do all of them. And some of them it's not going to be allowed. So it's getting permission denied. We utilize that as an administrator to tell us what processes or have some huge giant file opened up into memory. That's it when we look at processes and analyzing our system with processes. Any questions on this chapter? Any questions? Answer no in the chat session or, or too long. I don't know why I said too long. I was thinking about something else. Okay. Well, let's do another chapter. I know you're like, yay, another chapter, Professor Wade. We're going to do more. I got all this memorized. I'm keeping up with all the reading, so no problem. Okay, here we go. Chapter 5 is the file system. Now, I had a lab dealing with this, folks. I had a lab. Yeah, if you look at the schedule, we're supposed to be around 5 or 6. I'm probably going to, I don't want to overload you too much, but we went over chapters 3 and 4 and 5. And then I'll catch up next class by trying to do 6, 7, and 8. Okay. So after this chapter, some chapters are shorter than others. Some are longer. After this chapter, we'll go over today's lab. Okay. And the schedule. So one of the most important things about Unix, folks, is you have to understand the file systems, the directory structures. You have to know what is user, what is etc, what is var, what is home. You have to know how the operating system and where the operating system puts files. That's an administrator's job, just like a Windows administrator's. Windows administrators have to know the same thing. If you don't know how the operating system is organized, whether Windows or whether Unix, you're not an administrator. You're just a user. Okay? Thank you very much, user. Go back to your cube. We're administrators here. We know all, we see all. Okay? We are the creators of your world from a computer perspective. Okay. Shada, Linux isn't hard. It's the same as a Windows operating system. As a matter of fact, granted, I've been doing it a long time. I find Windows more difficult because once you learn Unix and Linux, it's the same across all the Linux versions. I'm going to show you something here. Let me show you this now. Here's the problem with Windows that I can't stand about Windows. Every time a Windows version comes out, version 11 is fixing to come out. I think it's out because I know they've run it. Every time a version of Windows comes out, they change their GUI. What you used to do is in a different place. You can't find it. You're a Windows administrator. you're loading the next version of the OS and you can't find where it's at because the wonderful world of Microsoft goes, well, let's change it. Oh, it'll make it better. No, it doesn't make it better. It just makes it more difficult. And you're having now to search what happened to this? Where did this go? Okay. I can't stand Windows. That's just me. I also can't stand with Windows that, I have these programs I'm loading on my system and I've got hundreds of processes running, little dinky processes sucking up my memory. Unix doesn't do that. It contains everything in a directory, a program, and then you run the program and then it loads it in memory. Program's not running, it's not using the memory. That's how Windows should work. If the program's not, if you don't need it, why do I need all these little dinky Adobe processes that, just because I loaded Adobe software? And then, you're going to have an administrator go, well, you can go in, because I talk with the lab technicians and like, well, you can go in and you can stop the service from running. And I'm like, sure I can. Do I really want to do it? No, I don't. Why does it have to do it? And so Unix has been, everything I'm teaching you now has been this way for years. Okay? Has been this way for years. You learn Unix and Linux and you're not going to have to worry about where did they move it? Oh, the ITSC directory. I think it's moved. Where's the binaries now? That's moved. I don't need a GUI that changes on me all the time. I can with command line and I know exactly where stuff is. And if it's a different, now, here's what does change. Let me show you what does change. What does change, and I'm going to bring up our site. Here we go. Go to Cool Links. And this is probably a little old now, but it's called the Unix Rosetta Stone. So different flavors of Unix. The commands don't change, but some of the configuration stuff changes. And let me see if I can shrink this down. Oops, no. There we go. This is put together by a person that there were all these different flavors of Unix. See, look at this. AIX, IRX, Linux, Mac OS, HPUIX. Okay, it's in there. I'm going to pop this into the chat session. But the main difference between these flavors of Unix, see all these flavors? Solaris, Sun OS. This Sun OS was before Solaris. All these different flavors of Unix. Well, what changes is some of the configuration files are different from each flavor of Unix. And I don't know if this has been updated or when the last time the author updated this. Let's see, 2014, so years ago. But I still have used this a lot in the past in my career. Why? Because the main changes that change from OS to OS is like how will you manage hardware. The commands might be slightly different from OS to OS. So watch this. Let's say that I get employed and I'm a Linux administrator and they say, oh, I have AIX as well. And you're going for an interview and you go, okay, I need to know about AIX with this company and Linux. And then I draw the table. Notice that now I just have AIX and Linux down here. So here we go. Is there any administration GUI? Well, yes, AIX has SMIT, SMITI, WSM. Linux has Linux Conf, Red Hat -config, DRAC-conf. And then see, look, it lists Debian, SUSE, managing users, user add, user delete, user delete. All right, looks like that's in common. Hardware configurations, PRT, CONF, LSCFG. Oh, looks like the hardware config commands are a little different from Linux to AIX. This is called a Rosetta Stone. And then here you get into read a disk label, label a disk, partition a disk. Notice MKLV, make logical volume in AIX. Over here, look, I can have fdisk, cfdisk. We're going to learn some of these commands. Debian can use mac-fdisk on a Mac. You got disk Drake. But what this does, and you'll notice that the commands deal with, there are variations between hardware management and basically some kernel parameters. Those are different. But getting around Unix and moving around like CD, LS, and the directory structures are pretty much the same from OS. They all have an ETC directory, every one of them. They all have a bin directory, every one of them. It's the same, okay? Let's see. Seth says, look up Linux Mint. If you like the GUI the Windows has, I'm using the Linux Mint. Don't have to use the terminal if I don't want to. I put Linux Mint on my brother's computer. He has never used the terminal. And running. Okay, so Seth, Unix people don't use GUIs, okay? Unix people, we are command line people, okay? We're command line people. Does Linux have GUIs? Yes, they do, okay? But a real Unix person knows command line. You know why? If you go to work as a Unix administrator, most companies, I would say 95% of all companies I've worked with, okay, don't use any form of GUI on the Unix system. They're operating in data centers. All of these data centers have predominantly Unix systems, Red Hat Linux, or you get some AIX, splattering of Solaris, and the others, but Linux is the de facto standard for data centers these days running web-based applications. There are tons of them, and they virtualized a lot of this now using virtualization, and we'll get to a virtualization chapter as well, but they don't run GUIs. We don't need GUIs. We just need the program to run that needs to be run, and that's why we don't use GUIs in the Unix administrator world. Desktop, you know, you find a splattering of desktops out there, 5%, you know, where people are interested in getting in Unix, so they put a GUI on, okay? Or Kali Linux. I've got Kali Linux. The programs that run with Kali Linux, a lot of them are need a GUI of some type, but for the most part, you're going to find data centers that don't use GUI, okay? That don't use GUI. But yes, there are, you know, if you're just getting into this and you got an old laptop, like I had an old laptop, load it with something, you know, Linux Mint. You can load Red Hat Linux. We're going to be doing that in class on your system. You can load, you know, like me, Kali Linux, which has the GUI. Okay. So anyways, these are some of the variations of Linux. This is called the Linux Rosetta Stone. And what it's doing is doing comparison between operating systems, different Unix operating systems. And you can go down through it. I used to use this for interviews. So if I looked at the interview and they said, we need somebody with Linux, but AIX is, AIX is, we're looking for that as well. But maybe they'll say Linux, you know, and AIX helpful. And then I would go through and look at this and memorize some of this. So if they said, well, have you worked with AIX? I have, but it's been a while. But they may ask me, you know, well, what's the administrative GUI for Unix? Oh, it's SMIDI. Oh, okay, there we go. SMIDI. What about if I want to add a user? You know, oh, well, user add works on both of them, you know? So you could literally spend an hour doing a little bit of comparison of Linux to AIX, memorize a few things so that, you know, I mean, you don't have to say, you know, oh, well, I know everything about AIX. You just say, you know, well, you know, there's slight differences. You can move around AIX just like Linux or other Unix systems. You know, mostly the hardware or administration changes a little bit between the systems from a sysadmin perspective. Okay. Okay. So the file system and Unix file systems, you have to understand. And that's a nice thing is that, Shada, they don't change. Okay. So they don't change. So let's see. I got just saying most people only interact with the GUI in Windows. You can only use the command prompt. It would be just as difficult, if not more. Actually, Windows administrators use PowerShell to write scripts to basically do quite a bit of stuff. Okay. Regardless of whether you're a Windows administrator or you're a Unix administrator, you're going to have to know some scripting. And that scripting for the Windows side is PowerShell. And actually, Windows is starting to come out and put Unix into Windows. So you may find one day that behind the scenes, the Windows from Microsoft is all Unix in the background. No, that's true. The average user isn't willing to learn, but that's why we're all in class here is to learn Unix. So, okay, so here we go. The file system. We need to understand that file system. We need to understand where, and regardless of whether it's Windows or Unix, you've got to understand where the file system. From a Unix perspective, it's across the board the same. So a file system can be thought as comprising four main components: a namespace, an API, a security model, and implementation, software to tie the logical model to the hardware. We also have absolute and relative paths. Okay. Who can tell me, just out of curiosity, what is an absolute path and what is a relative path? Let's start with the absolute path. What do you think? What's an absolute path? Yeah, that's correct. The exact path. Okay. It is the exact path. Okay. Or we often call it the full path. So slash my directory slash folder 2 slash folder 1 slash run it.sh. Okay. This would be the absolute or full path. Relative path. Who can tell me what relative path is? Yeah, Jesus, is not a shortcut. Seth has it right. The relative path is from where you are to where you're making the path to. Okay. Not necessarily a path from another file. It's where you're located. It's relative to where you're located. So let's say that I was in folder 2 right here. I did a CD and changed to this folder. Okay. If I did a PWD, it would give me a path that would say my dir folder 2. This is my relative path of where I'm at. But here's the key. If I want to run something there, I would run folder 1 slash run it.sh. This is the relative path to where I am at. This is the full path. This is the relative path because I'm located here. So see, notice that the absolute path has the full path. The relative path, well, that depends on where you're located at. You'll notice there's no slash in front of this because I'm in some directory that has book 4 in it. Okay. Now, let me ask you a quick question. In the Unix world, do we use spaces for file names or directory names? Yes or no? What do you think? Yeah, the answer is no. And some of you said we can, but it makes it more work. Jamie said that. Um, you know, the answer is no. Seth, you said we need the double quotes. Yes, you can do it, but no, we do not. Okay. I'm giving you best practices here, folks. If you want to do it, have fun with it because um, here's the thing. What about on the Microsoft side? Yes or no? Do Microsoft side often use spaces? Yeah, they do. Okay. They definitely do. Okay. And even I do. Okay. I will admit, I mean, if you look at my desktop, you will see there's loads of names with when you load programs. But in the Unix world, we don't do it. Notice here, we have to use these double quotes if we've got these spaces in here, which is what a couple of y'all said. And yeah, Seth, I was really asking, should we? Okay. Um, and I usually sometimes ask questions to just to see what people will answer. But the answer is we don't want to do spaces for this whole reason right here. You have to do this. And not only that, what do you think when you write a script? Let's say you have all these files and file 1, file 2, 3, 4, 5, all these files, and you're doing some kind of scripting that you've written. Do you think it's more difficult or less difficult if it's got spaces in it? What do you think? More difficult or less difficult? Yeah, it's a lot more difficult, folks. So don't ever use spaces. Let's see who said it. James said underscore. And so instead of writing this here, let me erase this. There we go. Let me erase this. By the way, I've been a Windows administrator as well, folks. So in my Unix classes, I do pick on Windows a little bit. I did Windows administration for about 10 years. Um, and man, I just didn't care for it. And I've taught the Windows servers course here as well, and I don't care for it. The book, by the time the book comes out and students are using the book, the GUI changes. And students are going, I can't do these labs, Professor Wade. And I'm like, why not? Oh, it's changed. And so now I was spending I've taught that class 3 or 4 times, and I always spend my time, having to go through the labs to say, okay, this has changed, this has changed, this has changed for the next version because they come out with a new release. But here's what we do: we go you can either use a minus sign or you can use the underscore, or how many of y'all have heard camel case? How about camel case? Anybody heard of that? Yes or no? Okay, no. Lisa, here you go. You use capitals like this. My excellent. Oops, sorry, that's not a capital. File. Okay, that's camel case. You can increase the size where the word is. So lowercase with a splattering of uppercase. Okay. And why do they call it camel case? Well, because you got the humps on a camel, right? So, anyways, I use underscores sometimes, James, and sometimes I use minus signs. I kind of like the underscores a little better. The minus sign kind of runs it, so I'm kind of partial to underscore as well. But sometimes I've done camel case as well because then it eliminates this. You know, I don't know. I can't say that because I've done a splattering of both. It just seems to depend when I'm writing the script what mood I'm in. Okay, but one of the things we need to know, and this was one of the labs that we did, And you should have learned this in the first Unix class, okay? The first Unix class is, here's all the different directories that you might see on a Unix system. And it varies a little bit, but some doesn't vary whatsoever, okay? And so here we go, ETC. Every one of them you'll find an ETC directory. This is where all of your critical startup and config files are. If you did not know this on an interview, I would not hire you at all. Now, if I said, well, tell me some of the important directories on a Unix system, and you didn't say /etc, I would be going, oh, okay, well, thank you very much. Have a nice day. The bin directory, a lot of those core commands are there, like ps or ls are in the bin directory. Dev directory, this is where all of our device entries are for disks, printers, pseudo terminals. Okay. And in the /boot, you get a lot of kernel files there. Okay. And then of course, well, there's the /kernel. Sometimes you may not see a /boot, you might see a /kernel. Notice here that they're giving us the different OS types. So all, or here, look, ls, okay, and the L is Linux and Solaris, but then notice here S, which is Solaris. So it depends on the operating system, but wherever it says all, it's pretty much all flavors. Like lib is across all flavors, libraries, shared libraries, parts of the C compiler. These are used by programs and the operating system for additional code to basically make available for our programs to run. Media, mounting files on Linux and Solaris. You've got MNT, Linux, Solaris, and AIX /opt. Back in the day, this is where we would install optional software packages. Okay, the opt directory was predominantly, where additional software was being installed. But the problem was that they started putting everything in there. So then later on, they started creating more specific directories and partitions. The other thing is, by default, the operating systems would put in a /opt. And if you didn't do a separate partition, you could fill up the operating system. The operating system. Here's that /proc we talked about today. /root, well, that's in Linux and Solaris is the home directory for the root account. /sbin, this was usually commands that the systems administrator would use. They were more administrative type commands. /stan, standalone utilities. This is HPUX. Temp, all have /temp. And let me ask you this. Well, it already says here. So when you reboot, anything in temp disappears. Here's the only problem with temp. This is funny too. Sometimes they'll take temp and they'll link it to memory. Okay, so that you're actually, the temp space is in memory. And temp only has a limited amount of space. But we had an alert going off on a system one time that was saying, hey, the temp disk space was filling up. And the operating system needs that temp, or else you can crash the system. It's really meant for temporary files for the operating system and maybe a tiny temporary. It's not meant for big files. And so for some reason, this developer logged into the system and decided to, this is where you get where a systems administrator versus a user. And the developer decided, well, temp means temporary, and I'm just doing something temporary. So I'm going to load it in there and created a database because it was going to be a temporary database, Oracle database, and put the database files into the temp directory. So you had this huge temp directory. Wasn't even huge. It was like immediately filled up, and our alarms went off because the temp directory was filled up. And luckily we got to it in time before it crashed the system. That's another thing. If the root file system fills up and the temp file system fills up, you can potentially crash or bring the system to its knees. That's why we often do separate partitions so that it doesn't fill up the root partition, the slash partition, or say temp. The slash user, well, this has secondary files that are needed. There's sometimes a user bin that has additional, binary files for doing OS, like PS minus EF. Sometimes you'll see this bin is really a link to user bin. They're the same. You've got user include, which includes, header files if you're using a C compiler. You got the library files. You got 64-bit library files. User local was also another place that they would stall, let's say, more local commands for specific, that maybe somebody wrote or your company's using. User share, so common items. You might have some libraries that are common. There's a user share lib, user share bin, maybe something your company created you wanted to put in there. User source, not widely used. User temp. And then var is another important one. Var is where all of the log files are, or spooling files, or more temp space. So var spool is for like print spoolers or mail spoolers. Var log is where basically you have log files, and var ADM is more log files. So you have all these log files predominantly in two directories, var ADM or var log. You'll notice var ADM all, and here you got Linux, Solaris, and AIX for var log. Okay, so all of these directories are very important for you to know if you're going to be a Unix systems administrator. Now, file systems. What if we need a file system? Let's say for our some department, they want to load a database server, and so or create a database server, and they need something called /data. Well, we can create that file system, and then once we've created it on the disk, well, then we then mount it to the disk. In this case, mount dev SDA4. That is a partition on disk SDA called /users. There's 3 files here: FS tab on Unix, VFS tab on Solaris, and ETC file systems on AIX. These 3 files tell the operating system basically what to mount when it boots up. If we go and look on our system, cat etc fs tab, here we can see the dev is the device, and notice that this is VG. This is a volume group. We'll talk about that in a minute. It's a volume group. And what we do here, look, here's the root. When it boots up, it's saying mount this up. This is the file system type. Now, let me ask you a question. If I go buy a disk drive, just a regular disk drive or SSD drive, and I plug it up to my Unix system, or I plug it up to my Windows system, is it going to be able to immediately start saving files to that disk drive that I just bought? Yes or no? What do you think? Yes or no? And I'm not talking about where you bought a little box that said, hey, you can back up your data or something. I'm talking about a real disk drive, okay? I got one here. Hold on a second. Here we go. Right here. This is a disk drive, right? I don't remember if this is an SSD or not. No. This is a SATA drive. SATA HDD, okay? This is a hard disk drive right here. Came out of actually my laptop over here. Came out of it. It's pretty small, pretty thin. But if I bought this right from the manufacturer and they shipped it to me, or I bought it off Amazon, and this is what they gave me, And let's see, most of you said no. And okay. So a couple of you are yeah, okay, so no. Okay. Even if you try to mount it, it is not going to work. It won't work if you mount it either. Whether it's on Windows or whether it's on Unix, it doesn't. Why? Okay. Why does it not work? Easton has it correct. Easton, I'm giving you 50 points for that. You have to basically create, first off, it's got to be formatted. It's got to be formatted. Okay. Meaning that when it comes, it's just raw media. You have to go into it and say, well, how do I want to break this up? Do I want to create one giant partition? Or do I want to create multiple partitions? So you've got to format it first. Now that you've got it formatted, you said, oh, slice it and dice it up into 6 pieces. Okay. You now have to create a file system on that 6 pieces. Every operating system has a different file system type. Okay. That operating system only works with that file system type. Now, saying that, some of y'all probably say, well, wait a second, you know, I can stick my Unix file system and yeah, but used to you couldn't. Okay. So, you know, they've just written programs now that read other file system types. Okay. It depends. Seth, so you're saying FAT32 works with Linux and Windows, right? A lot of them do now. It depends on the operating system itself. But hold on. I'm going to go to my friendly neighborhood Wikipedia. Okay. And let me see if I can find it out there. There used to be a really nice one on Wikipedia. It looks like they've modified it. I'm going to say, there we go. That's what I'm looking for. Okay, so let me ask you this. How many file system types do you think there are, folks? How many file system types do you think there are? 20, 30, what? Or tons? Yeah, tons. Tons. So in order for that operating system to be able to talk to the disk drive, it has to have a file system that it understands. In order to be able to mount it, this little disk drive has to have a file system that, well, it understands. Right now, this is NTFS. This is a Windows file system. It was formatted with one partition, and then we created the file system on top of that. Well, this is NTFS for Microsoft Windows. Okay. But here on Wikipedia is a list of file systems. Look at all of them, folks. Tons. Okay. Now, here you can see, look, you know, if we look at EXT2, EXT3, and 4, well, these are, let me see if I can zoom in a little bit. There we go. The EXT2, 3, and 4, that's for Unix. Okay. That is for Unix. Let's go down through here. FAT. FAT is old style Windows. Started with the DOS operating system. And then they came out with, oh, okay, FAT 16 for 16-bit, then 32. And nowadays, what they do is NTFS, new technology file used for on Microsoft's Windows NT. So they have newer operating system than FAT. That's old style. Here, look at this. Here is HFS, hierarchical file system for Mac OS. You know, all of these different, even sometimes vendors would write their own file system that was supposed to, and it cost thousands of dollars. Here we go, Veritas file system. I used to install these on Solaris and HPUX and Linux systems. It was supposed to be a file system that sped everything up. I don't even know if it's still used. I haven't used it in years. Let's see. 19 renamed Veritas. So it'd be interesting. I might Google it one of these days to see if they are still out there. ZFS was Sun Microsystems. Okay, Sun Microsystems. But you have to partition the disk physically, which is formatting. Once you do that, you create the file system. Once you do that, you mount it up. But let me ask you this. If I mount this file system up here and reboot the system, is it still going to be there when I reboot? Yes or no? Yeah, Seth, on Windows, it's NTFS. And on Unix, it's or Linux, it's ext4 on Linux systems. And, you know, and then FAT is like old Windows. So you're correct. You know, yeah, no, that's correct. All of y'all are right. It's gone. What you have to do is you have to put it in this FS tab and tell this FS tab or VFS tab if it's Solaris, or file systems if it's AIX, and you have to tell that right here to mount. See how here, look at this. Here's the home directory, folks. I created a volume group. Here's the file system type. Okay. And it's going to mount. And then over here, usually over here, you tell it whether you want to, what order you want to mount it up. You can order, mount it, the first one, the second one, the third one. So, and then as well, you can say if you want to do a file system check when it boots up, check the file system. Okay. Now, when we mount something up, if we don't want it up there, if it's temporary, we do an unmount command in the Unix world. The -F does a force. Here's the thing, what happens. Sometimes if users start accessing this, we can't unmount it. We'll say unmount, it'll say someone's using it. Sometimes we can do an fuser command of that /user and see how it gives us right here, these usernames and the process ID accessing it. So it's process ID and username that is accessing this partition. And then we would call the user and say, hey, can you please get out of that? Because you don't want to kill it. You don't want to do the force. If you do the force, well, then it kicks them off. Now, on each file system, you have different file types. We've looked at that when we do the ls command. You can have regular files, directories, character device files, block device. Character device files are device files for like keyboards, characters. Block is like disk drives, local domain sockets, pipes, and symbolic links. We've seen that. It's an S. So here we go. Whenever we do that ls, that first character tells us the type. So take a look. D for directory. User include as a directory. L for a symbolic link. See, you got the arrow there pointing you to the real file. Minus, meaning a regular file like gzip. And by the way, it could be a binary. Doesn't necessarily mean you can edit it. It just means it's a file. In this case, this is a binary file we would execute. And C is a character device. See, TTY, okay? We would have a keyboard. We can also, let's go take a look really quick. Change directory to dev. I'm going to grep for SD. And notice, see where it says B? That's a block device. And SDA is the disk drive on this Unix system. And the partitions, folks, are right here. 1, 2, and 5. Okay? Those are the partitions that got created during the format process. Okay? So once again, here are some of those first character symbols. D for directory, C for character device, B for block, S for a domain socket, named pipe is a P, and symbolic link is L. Here's how you create them. Make dir to make a directory. make nod to either do a character or block device file, and then make nod for a named, and a socket is usually created in some kind of program that you're writing. And then here, ln minus s for the symbolic link. Or if we remove this, it would be a hard link, but it would just be directory or a minus for that regular file. And here is how we would remove all of these. Permissions, we talked about permissions. If we look at permissions, it's read, write, execute. And what you have is owner. Let me get my pen out here. You have owner, group, and other, or also called world. Let's see, I got a question. Will it be ext if you reformatted it? No, if you're reformatting it, that's kind of repartitioning it. You have to do a make fs. We're going to see that here in just a minute. There's a way to do that in Unix, doing a make fs command, make file system. That's what it stands for. So here we go, file types and permissions. Okay, so every file by default has this owner, group, other privileges. Now we can set that using a change mod command. For example, 711. And this is where you have to know a little bit of binary, folks. A little bit of binary. Because see, this is being done by binary. So if you look at it from binary, and I did a 711, well, a 7 is read, write, execute. Now, you should have had, usually by the time you get to here, you've had some classes with binary. Once again, you have to know the binary placeholders, 1, 2, and 4. So a 1, 1, 1, well, if you add these up, it equals 7. A 1 would be execute. How do I know? Well, 4, 2, 1, 4, 2, 1. Okay? And that's what they're showing you down here. 0, 0, 1 is execute only. So if I did a 755, it would be read, write, execute, and then read and execute. I would be giving me, the owner, full privilege. I would be giving the group the ability to read and execute, and I would be giving the world read and execute. Okay? Okay. Now, remember how I said set UID and GID. We want to give them higher privileges. Well, we do that by setting this to 4 and 2. So if I did a change mod of 4711, I would be basically giving this owner set UID privileges. Okay. And the other two could only read. They couldn't do, execute. They could only execute. They could not basically, make changes to it. Now, what about if you want to basically, when you create a file, have those privileges created the way you want them? In other words, you don't want to have to do all of these change mod commands. Okay. Hold on. Let me get my pen. You don't want to have to do all of, apologize. We're almost done this chapter, then we'll move on. You don't want to have to do all these change mod commands like, okay, I create all these files, 1, 2, 3, 4 files, and now I got to go do change mod 750. See, 0 gives no privs to other. My file, and then have to go down through all the files and do the change mod command. So you can set what's called the UMask, okay, to give default permissions to the files that you create. For example, if I type in, and by the way, you can set this in your startup config files, like your .bash rc. You can set this in a .bash rc. Every time you log in, it sets it to UMask 027. Now, here's the only thing that I don't like. Why they didn't just use the same format as the change mod, I don't know, okay? Sometimes I think, well, they just want to be, difficult, okay? So, UMask allows permissions for the owner, but forbids write permission to the group and no permission. It's the inverse, folks. Don't ask me why. I think it's crazy, but it's the inverse. Look, a 0 means read, write, execute. A 2 means read, execute. It's the inverse of the other. This means nothing. Don't ask me why, but you just need to remember that the UMask is the inverse of the change mod. That's the way I remember it. The UMask is the inverse of the change mod. So I'd love to find the guy that wrote this and say, why'd you do it that way? Well, I wanted to make sure they knew it's different. Why not just say, hey, I want my permissions to be this, and it's the same as the change mod? It would have made 10 times easier, but they didn't. Does everybody understand how the UMask is the inverse? Answer yes in the chat session. What that means is when I create a file, it's going to have this permission. Now, let's say I didn't do this and I created the file. Well, I would have to do a change mod 750 to my file. That's what I would have to do. This would give me, once again, read, write, execute, and the world gets nothing. So the change mod command works like this. The UMask is the inverse of change mod. Okay? I know it's crazy. I'm not sure why they did it. Okay. So Linux uses, depending on what version, today we do ext4, but you might find some old versions using ext2 or 3. But there are additional attributes, and you can use ls attribute or change attribute to view and change them. For example, never update the access time, allow writing only in append mode, force directory updates, no backup, make dump ignore this file. Meaning if I want to dump the entire disk, this would say ignore it. Make a file immutable, keep a journal, force changes to be written synchronously. I rarely use these myself. I just use the defaults. Access control lists. Virtually all non-Unix systems use a more complicated way. Hint, what they're saying here is Windows, of regulating access files. Access control list, well, each file or directory can have an associated ACL for the permission. Remember, we talk about permissions from read, write, execute, read, write, execute. And in the last chapter or the one before that, we talked about how that really doesn't give us granular permissioning. One user, one group, and the world. That's it. That's old style Unix. They had to come up with a better way of doing it. But a lot of that had to do with the file system type and what the file system could actually do. So under Linux, they allow us to use get FACL and set FACL. So get these access control lists, file system access control list, and set. Solaris, same thing. Look how the commands are the same. HPUX, a little different. AIX, a little different. Okay, ACL get, ACL put. But take a look. This is what I want you to look at. Notice that, here, how I can have user read write, but look at this, user Trent. So I can give Trent a specific user. I can give the file's owner, well, that's old style, but now I can give a specific user some additional access. And then look at this, group, and then a specific group. This group I gave read and execute. This group I give read write. So now using access control lists, I can use multiple users and give them different access, and multiple groups and give them different access. I mean, look down here. Here I have this file called temp example. Here I set the privileges, and all users have read access, but Trent has read write access. And I should have said the owner has read and Trent has read write. That's kind of funny. Okay, Garth owns the file, but Garth's only allowed to read it. Okay, Garth can't write to it, only Trent can. And then group that owns it, Garth, can read it. So Garth can't see here. Look, Garth is the owner and Garth is the group. But Garth can only read it, and as a group, Garth can only read it. And the admin group can read and write to it. Okay? And then the mask is all but the owner and others. Okay? So look at that read write. You know, poor old Garth is like, it was my file. I created it. Okay? So now we have the ability to do a ton of stuff. NFS is network file share. It allows us to share files across the network. And we can also set ACLs on NFS, the files that we want to share going across the network. Look at some of this. We can set read data on a directory. We can set write. We can set, do we want to allow pinned? Meaning you can create file names, but you can't write or append to the existing file or directories. So we can say read only, we can say you can write, or you can append only, meaning something's there, you can, so you can't create a new directory, let's say. You've got read named attributes, write named attributes. Are you allowed to delete children within the directory? Can you execute a program? Okay. And there's others here. Can you change ownership? Here's some inheritance flags. Now, what's inheritance? Inheritance basically means, what do the children below inherit? So one of the other things they looked at was, let's say I got a directory, and here is directory A. And under that, I create a directory B and a directory C. And under that, I have a bunch of files and files under these. I might even have another directory under here, directory D. And let's say I set the permissions here to, read, write, execute. And I'm not going to give an ACL example. I'm just going to go with old style to give you the point of what inheritance is. Read, write, execute, read, execute, and that's the privileges of directory A. With inheritance, I can say, hey, if I create another directory, let's go ahead and use the inherit. We're going to inherit these privileges. And so using ACLs, we can say below us what we want the permissions to be if someone creates something, edits something below us. The other thing we have the ability to do is go ahead and, see how it says propagate this ACE, okay, our access control list, to newly created files. Propagate this to newly created directories. Propagate, but don't apply to the current directory. And propagate to new subdirectories, but not their children. We could also go and manually set this directory here to say, oh, actually, I'm going to write it down here. We could say read, write, execute, dash, 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 meaning I don't want the group to have access. I only want the owners or multiple owners or users to have access. And then these below would inherit the same permissions. All of this we can set, okay? They're just showing you here how, we're seeing, add subdirectory. And it's saying right here, owner, list directory, read data, add a file or write data or add a subdirectory. We can append data. We can write attributes. We can execute. We can write attributes. We can write ACLs. It's telling you what the permissions are for this var temp example directory. Okay. And see, I can do it by owner, by group, and by everyone. So it's pretty nice with ACLs that we can go. And look at this. Here we go. Look, deny, allow. So see all these different permissions down here. So we've got read, write. We've got append, read attribute. But we can go in and basically have groups and different owners with different names and give them all of these different permissions that you see down here. And then this one just lists the change mod on a Solaris. One of the other things is here we're doing, replacing. This is actually adding an access control for user and Ben, and we're basically saying allow access to var example. And that's it for permissioning. We are going to get into a chapter on storage, which I will then walk you through. I'm not going to get into it into it today, but we are going to walk through. I just briefly mentioned you got a partition and you have to create those file systems. We will get into that in the storage chapter where you're going to learn how to go and do that, okay? Any questions over chapter, what is this? 5, sorry. Chapter 5. Any questions? Answer no or feel free to ask a question. Okay. Let's take a look at the labs, folks. Let's do the schedule really quick. Then I will go for the lab. So today is, oops, hold on. Need to go. I think between the next semester, I'm going to remove a lot of stuff. Here we go. So today is the 11th of September. I'm one chapter behind, which is chapter 6. So I'll try and catch up with that next Saturday. We went over chapters 3, 4, and 5, which means now by next Saturday, you want to have up to chapter 5 quiz. By next Saturday, you want to have up to chapter 5 quiz. You should already have up to chapter 1 and 2 quizzes done. But I went over 3, 4, and 5 today. And by next class, you should have 3, 4, and 5 quiz done. On the labs, well, you should have that pre-Linux lab done. And you should by now be finished with UNIX lab 1. And for those of you that maybe missed last class, I go completely over this lab. Okay. So we'll go watch the video for the last class, and we're fixing to go to UNIX lab 2. You also should have reading up to chapter 6 in your reading. By next week, you want to have chapter 7 and 8 read in the textbook. Any questions on where we're at in the class or the schedule or what you should have done? By now, you should have chapter 1 and 2 finished, lab 1 finished. By next week, chapter 3, 4, and 5 quiz, and UNIX lab 2 done by next week. Okay, any questions? Nope. Okay, folks. Well, let's go through the lab. I am going to log into Blackboard as soon as I can find it. Let me get rid of that. There we go. Okay. So lab assignments, we have the shell scripting lab 2. Once again, I'm going to go over this again just really quick. What I'm looking for when you submit a lab is I'm looking for this. And oh, by the way, folks, please put the labs in line with the question. I'm going to say it again. Please put the labs in line with the question. I don't want to see like, and let me give you an example. Let me download this really quick. Here we go. So here we go. Here is lab 2. There are 5 exercises. Please don't go down here on the next page and submit your snippets down here. I don't want to have to interpret which snippet goes with which exercise. Okay? Please put them in line right here. Okay? Please put them in line. And what I'm looking for is this. Let's say, let me see where I've got some script. Usually these temp directories. I need to get rid of these too. Okay, so here's a script. So first thing, cat. Once you finish the script, don't show me VI either. I'm not interested in VI. Okay, I don't want to see VI. I want to see, matter of fact, what's nice is typing clear. Clear the screen. So I want to see cat s6.sh. Bang, there it is. That would be the first snippet. Okay, because I did grade some of your assignments. And so I'm going over, what I saw. Give me 2 seconds here, folks. Let me get my snipping tool. And let me just do a quick save here. And actually, I'll do one more snippet because it looks like, oh no, I won't do another snippet. Okay, here we go. File, save as. Apologize for the delay here. Give me 2 seconds. And UNIX 2. Today is September 11th. Okay, and let's see. Jesus says, would you like us to still use an LS minus AL before the class? That's fine as well. That just shows me the name. That's awesome. So here we'll do that. LS minus AL. There I see the script. Cat s6.sh. Bang. Now, depending on the script and how big the script is, you might want to take it in 2 snippets. Now, if you remember that first one, so here we go. You got the LS. You could bang, and there we go. And once again, please put it in line. There we go. And then show me it works. Folks, I do look through this. And if I see that it doesn't work, well, it's not a script, So then run it. And let's see, what does this one do? Oh, I don't want it to back up. This is a backup script. Let me find an easier script here. Let's go to scripts. Is that what I did? Yeah, that's what I did last week. Here we go. Show me it works. And then we take a snippet of that. And yes, I apologize. It is a different script. Take a snippet of that. There we go. Bang. Now, this one was an easy one, right? This was from last week. So if we did a cat s1.sh, bang, and then if you run it, Bang. I'm looking to see that it works. Now, I didn't count off this last for those folks that in, but the other thing I mentioned was, let's go look at S7. Notice we have if-then clauses. If there's an if-then clause, I want you to do every single one of them. In other words, this is a regular file. This is a directory. This is some other file. And I mentioned this. Anytime you have an if-then clause or you have a case statement, you have to do each one. This is how we test our program out. So I want to see each one. But do inline snippets. I want to see the question, and I want to see basically what it is. Don't put it all down here at the bottom, and then I have to figure out, okay, let me see, which one does this? Does it match with this one? Yeah. Oh, okay. Please. Okay. So let's go over the scripts. Give me 2 seconds. And one of the things, folks, is I'm not going to, like last time was really kind of an introductory of me, going over stuff. I'm just going to go over the script. I'm not going to VI it, pop it in there, and run it this time. I will go over it in detail. So give me 2 seconds. Okay. So I'm ready. So let's take a look. Here is lab 2. Write a shell script that displays this script will exit with a 0 exit status. Be sure that the script does indeed exit with a 0 status. Now, here's the folks. An exit status, does anybody know? Answer in the chat session. What do we use? Why do we use exit status in a shell script or any kind of program? Why do we use an exit status? Anybody? Yeah, Nicholas says to help debug. Lisa, not so much to end it. James, not to so much exit a loop. It is really there to give us diagnostic information. Yes, it is. We do use it for exit a loop or end it. Both y'all are right. But a lot of times we use the exit status of some type to give us diagnostic information, okay, to understand, so let's take a look. How many of y'all have Notepad++? I love Notepad++. So here we go. Pretty simple, right? I mean, all we're doing here, once again, is we put the bin bash up here to say, hey, everything below here is bin bash. And here we're just echoing something and giving it an exit 0. Exit status 0 is going to tell us whether or not it basically exited in an orderly process. But if I have if-then clauses or other clauses, I can actually put exit status to let me know where it exited in the program, to give me diagnostic information, to help me debug it. Okay, let's look at the next one. And hold on. So we're just going to go down through these, once again. Write a shell script that accepts a file or directory name as an argument. Have the script report if it is a regular file, directory, or other type of file. If it is regular, exit with 0. If it is directory, exit with 1. And if it is either type of file, exit with a 2. You've already written this, folks. Can everybody see this has already been written from the previous lab? So all you're really doing is putting an exit status. Once again, why do we use exit status? We use exit status because we want to know whether it was successful or where along the line it actually, and we can use this exit status for either success or failure, either or. You're just exiting the program at a particular point. And then exit is either going to say, hey, it succeeded or it failed. So here we go. Notice it's the same program that you had. All you have to do is go and look and see whether this was 7 or 8, and then basically go through and just look at this. Add the exit commands 0, 1, and 2. This lab is to teach you how to help you diagnose some of your programs. Okay, if you're writing. Next one, write a script that executes the command cat etc shadow. If the command returns a 0 exit status, report command succeeded and exit with a 0. If it returns a non-zero, hit do command failed and exit with a 1. So now we've got a failure. Let's take a look. 2 seconds here. These are pretty easy scripts. There's really nothing complicated. So once again, cat etc shadow. We're just catting it out. And then what we're doing is checking the exit status. Okay? Whenever you run some type of command in Unix, it is in the background recording whether it was successful or it didn't work. Okay? And yeah, Lisa, that's exactly right. We're now adding, see, look, we're just doing a cat. Now, let me ask you this. Is this going to be a success, folks, or a failure for you to try and cat the etc shadow? What do you think? Yeah, it's going to fail. If you've done the lab, the shadow lab from the previous one, it's going to fail because we don't have permission. I mean, watch, cat etc shadow. It's a failure, permission denied. So in our scripts, when we write them, we can easily look for, see how you're looking for this dollar question? Well, the dollar question is a variable that is the status of the previous command. So this command failed, and the variable for that status is dollar question mark. Basically, you're saying, hey, what was the status of the previous command? If it's equal to 0, meaning it did an exit 0, well, then the command succeeded. But if it failed, else, the command failed because it didn't exit with a 0. Sorry about that. Give me 2 seconds. There we go. So it didn't fail. I mean, it didn't succeed, so it failed. And then we're going to put that little exit status out there. Okay? Let's go look at the fourth one. By the way, if you have any questions, if when I'm talking to you about these scripts, if there's something like, well, is this there? Why is that there? Let me know if I didn't say something. See, equals 0, because what's going to happen is if it succeeded, the exit status is going to be a 0. And if it failed, it's going to be a non-zero, a 1, okay, or non-zero. And then here, we're just exiting our program with a status. That's all we're doing. You know, if you wrote a big, huge program, you could check the status, and then you might have a different code here. You might exit 245 so that you could then understand, okay, it's exiting at 245. Let me see. Oh, it's that if-then clause there. Okay, so let's go. Exercise 4. Write a function that displays the number of files in the present working directory. Name the function file count. And if you use a variable in your function, remember to make a local variable. The WC utility is used to count the number of lines. Now, let me ask you, what is a function? Who can tell me what a function is before I pull up the code? What is a function? In scripting, what is a function? Anybody? Lisa says it's an operation. I've got a predefined set of instructions, an equation. not so necessarily an equation. Okay. Well, let's go take a look, folks. Jesse says a function can be called and predefined instructions, an action. Okay, so hold on. Let me pull this up. It is a named reusable chunk of instruction that can be accepted as an argument. Easton, that's a very good one. That's probably the best, folks, there. Easton says it's a reusable chunk of instructions or scripts that can accept an argument. Okay, so now in this one, I'm going to talk a little bit about how do we script where it looks nice. And I'd like you to start using this format. So notice now I've got a bunch of verbiage here. Okay, see all of this verbiage. And let me see here. Hold on. Give me 2 seconds. I want to pull up. Give me 2 seconds. There we go. Sorry, folks. I modified this one, so I'm going to show you the unmodified, and then we'll discuss this one. So give me 2 seconds. There we go. Okay. So this is a function. What does a function do? Because I want to explain function to you, and then I'm going to go back. A function basically is a piece of code. Okay. And Easton described it reusable chunk of instructions or a reusable piece of code that can accept an argument, or Easton, it also sometimes doesn't accept any argument. It's just a piece of code. So here's the actual main program. This says, hey, I want you to execute a piece of code called file count. We could do a lot of any kind of functions, but why do a function? Well, because we're going to run this piece of code multiple times in our script. I mean, I could have lines and lines and lines of script here, and I'm going to call that function 2, 3, or 4 times within that piece of code. Okay, it's called a function. So in this case, I have a function called file count. And these curly brackets separate and identify the ending and the beginning. So this is the beginning of the code, and this is the ending. In this case, I don't need to pass it any variables. I'm just literally calling that piece of code. We could also send some additional variables to the code. Okay, we could send some additional variables. In this case, we want to count files. So this is called a local variable. This local variable is only going to happen within the function, meaning number of files is the variable. And we're not going to see that number of files if we were to type in, if we were to type in additional code down here, that number of files couldn't be used. It's within the function. It's a local variable. If we want a global variable, it would have to be down here. Okay, that would be global, and that variable would go through, the entire program because it's a global. So there's global variables and there's local. Local variables are isolated to the function. So what are we doing here? Well, we are calling a function called file count. That means the code is going to jump up here to the function, and it's going to go number of files, which is a variable, equals ls pipe wc minus l. And I showed you this command. There's another way to do it. We could have done it this way, local. This is the way I normally do it. If you want to do either way, I don't care, but I use these. Notice 2 ways to do it. Either way is fine. This is basically, one way to execute something and put it into a variable. I like to use this method. I've used it for quite some time. And the reason I use this method is just because I can easily see, okay, I'm executing a command here. Okay. You can do either or, folks, either or. But you're doing an LS and a WC. Now watch. So I'm going to do an AL. You can see I got in there, but if I do a LS, WC minus L, which means do a line count. WC is word count. And L, it's going to count. And there we go. I got 13 in there. Let's see if that's right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It is correct. Okay. If I do an LS, there we go. There's 13 of those. And I'm piping it to WC, and it is going to then count them and come up with this 13 right here. And then what's the next thing I do? I say echo number of files. So when I run this, it should just print out a number of files, 13. Make sure it's not 1, folks. When you run it, make sure you got something in there so it'll actually count it. Now, let's go back to this. It's the same program. Here's the function right here. But what I was showing the class here is when we write a script, I've been showing you some scripts that look like this. Just the script, man. Anybody ever see the old FBI shows? They go, just the facts, ma'am. Someone would embellish and they'd stop them. Just the facts, ma'am. And so in the scripting world, or even in the programming world, we want to put it in a nice format. So I'd like you to start doing this. Okay. So, you're thinking the backtick is deprecated way and not POSIX compliant. Well, it's worked in my scripts for many years, and so they can deprecate all they want as long as it works. That it works for me. Okay. So anyways, look at this bin bash, but I put this set X up here because this is a way to get diagnostic information. Now, here, what am I doing up here, folks? Answer in the chat session. What am I really doing right here? What is that? What do you think? Why should I put this in my script? Yeah, it's comments. So look, this is the file count script. This script counts the files in a local directory. Author, Professor Wade, version 1. Okay. And then if I go and make changes, I do version 2, and then I put a date. It may even be version 2 was, by, Joe Smith. Okay. And then I document. Look, in the scripting world, we put functions at top. Okay. Easton says version control and blaming. So, that when it doesn't work, we can say, Joe, what did you do? But we put functions at the top, folks. This is just the way, programming languages, same way, functions at the top. And then we identify the function. This function counts files. Now here, I added another function. This function moves files. You document. Next, once you have the functions at the top, notice how I've got the functions separated here with the curly brackets. We put our global variables. Path equals, as an example. Maybe I got a different path. Number of files. Maybe I wanted to set a different global variable. This is a local variable, and maybe I decided to use a global. And then we actually put here, main program starts here. And you might document calling the file count functions to count files. Here we go. There's the function call. I'd like you to start documenting your scripts just like this. Now, why do we want to document like this? What do you think? Besides version control and blaming, I do like that one. Why do you think is another reason we should document all of our code like this? What do you think? There's a big reason. And I'm going to tell you what I didn't do in my career. I tell you, see, I'm telling you my mistakes so you don't make them. So James says to remember and to see what's happening. Anybody else? Tracking, monitoring changes and errors. People can understand what's happening after you leave. That's a big one right there, Easton. But there is one other reason. That is the second biggest reason. There's one other bigger reason. Anybody want to hazard a guess? How about so you can understand your own program? So I wrote this program, this script that audited all of the Unix systems, like hundreds it could do, and would pull in the OS versions, the applications loaded on them, the amount of memory, the amount of CPU. It was a big auditing program I wrote, and it had lines and lines of code. I sat and wrote this thing, and then, I don't know, it was like a year later, I think, or 6 months later, the manager comes up, and my manager, and says, hey, do you think you could add this? Some people are asking if they could get current CPU and on it. Oh, you mean? And I'm like, oh, you want live data? Like they click on it. Yeah, we want live. Could you, and what it would do is it would pull all that information. I would run it on a web server, and it would pull all that information and pull it into like a wiki doc. And so then we could, in an Excel format. So instantly you could go and see, okay, you just look down the column. Is everybody up to the same patch level? Does everybody have the same apps loaded? You could literally use this, and it built multiple pages. You go to this page, it would create a hyperlink, go to this page, pull up additional information like on all the applications. And it was probably, I would say, script wise, one of my biggest scripts that I ever wrote. And so now they wanted it live, meaning, okay, here's the current CPU, click on it, it goes out, grabs the CPU for that machine. And I said, sure. And I hadn't looked at that program for that script for 6 weeks. And I'm telling you folks, when I went back to it, I didn't do all of this stuff. Yeah, I listed this stuff at the top, but I didn't look, I didn't put, calling the file to count the files, doing this. This function does this, and I'm like, okay, I'm calling this function. Man, what was this? And it was like looking at somebody else's code, literally, because I hadn't been there. So you want to document for your own purposes, okay? So that you can go in if it's 4 months later and interpret your own work, okay? That's the biggest reason right there, to document. And so as you're going down here, if there's an if-then clause down here, you want to, as part of that if-then clause, you want to say, well, why are you doing it? What are you checking for there? Checking stuff. Okay. So try to document some of yours in this fashion. Functions at the top, global variables next, main program starts here. Okay. So I'm curious. I know I got some of my programmers here. Do they teach you any documentation? How to document at all in your programming classes? Those of you that have programming classes here, they teach you documentation? Oh, they do? Okay, awesome. And did they teach, just out of curiosity, did they teach this kind of style or format, documentation, what your program does at the top, version control, the last date that it was operated on, functions at the top, you know, and then global variables, and then your program starts. Just curious. Okay, last one. Modify the script from the previous exercise. Make the file count function accept a directory as an argument. Ooh, okay. More description of code and less emphasis on version control and dates. Ah, okay. Well, there are systems out there, Easton, that I used to work with one that do the versioning control for you. So you can go and see what versions the files are out there. They keep track of it all in some companies, but it's nice to have it at top, because then you have to go to another tool to actually figure it out. You know, if you just see a file there and they have no versioning information at the top of it, you'll then have to go and look, you know, at that tool. So here we go. Modify the script from the previous exercise. Make the file count. Ooh, now we're making it accept a directory as an argument. Next, have the function display the name of the directory followed by a colon, and then display the number of files on the screen. Call the function 3 times. First on the etc directory, next on the var directory, and finally on the user bin directory. And here you can see some example output, except you're going to have 3 directories. Let's go take a look. So here we go, pretty easy. So here, function file count. Notice dir equals $1. So all I did now is I created a variable, and the $1, well, that is here. If I wanted to, I could literally put other stuff in there. I could say, you know, local dir equals $1. I could do local file equals $2, you know, and I could just keep on going and have more variables, you know, here if I wanted to. Okay. So here, all I did, if you really look at this, is I just added a variable that could be input when we call the function. I then put the variable here. And then I added an echo statement that said echo $dir, so it's going to list this $dir, colon, and then echo number of files. Okay, and so when it runs, it's going to look just like this, etc colon 85. And then I've got you doing file count etc, file count vir, or /var, vir, /var, and file count user bin. So if I do a ls of /etc and do a wc minus l, I should see 223 in your script. Okay. Any questions on, this is the last one. Okay, the very last one. So you got 5 of them. Once again, please put, you know, A, cat the script out, and B, you know, put it in line, please, in line. Okay. Any questions? Any questions? And by the way, folks, you know what I used to do? I used to, this was my template. I would actually have this as a template. And what you can literally do a lot of times is I would have this all set in a template. I wouldn't put this in there, you know, like I would have one function as an example, and I would have this, the global variables would already be set, the main program already set. I would have my template already, and then all I would have to do, and the version 1 would be in there, and all I would have to do then is go and, you know, put up here what the name of the script was, and start coding. So I already had my templates that I would put in this format all the time. Okay. Okay. Yeah, Daniel, not until you get to work on it yourself. Okay. So once again, folks, this is up there. If try it doing it yourself. Okay. And if you can't, you can always, I will get this video up maybe today, but I'll try to get it up tomorrow for this class. I mean, usually after this class, it's my weekend. So the latest would be Monday morning. But I think last week I put it up that afternoon because I noticed it takes an hour or two to generate once we end the meeting. Okay. But, you know, you can always go and take screenshots of this, you know, and, you know, do it. If folks, if you're copying this, just like I'm showing you here, just make sure you understand the way it works. I don't want you to do a script and then not understand. Now, I did notice a couple other things with some folks. It has to run. No sense in submitting to me. If it doesn't run, you're going to get a 0. Okay. Now there's 5 here. So if you get 4 working and 1 doesn't work, I'll do, you know, that would be like maybe 1.5 points or something like that. But if it doesn't work, okay. So some of the things that I saw where it didn't work. One of the things that I mentioned to folks was, and I'm going to mention it again, is VI, your .bash RC, and at the end of the bash RC, add this in, folks. Path equals the dot. If you don't have the dot, it doesn't search your directory. So I saw 1 or 2 folks where they were trying to run the script and it said file not found. It can't find it because the path isn't there. And I went over that last class and I said, go into your bash RC, go to the bottom of it, you do an O, and remember, there's a cheat sheet for VI. You do an O, that's on Blackboard, okay? Under cool links, there's a cheat sheet. You do an O, and you just enter exactly what you see here. You enter path equals : export, and this is, export path, and, you know, it should then, give you, watch this. You do have to log out and back in. But if I go env, grep for path, look in your path. Now, I made the mistake. I did 2 of the config files, so it's doing it double. But there you go. So it immediately knows to search my local directory. See how I just did s1.sh right here? And by the way, I'll show this next, but if I go look at that script, watch this, folks. See how I have this set-x? Well, that set-x shows you diagnostic information as you run it. We'll get into that. That's another script, group of scripts. But s1.sh, and there it echoes it out. Now, the workaround, which a couple of you figured out, is to do a ./s1.sh. Okay? Bang. Okay? So that's the other way. You give it full path. This is full path. Okay? Doing the S1SH, that is absolute path. Okay? Although I shouldn't say that's full path. This is absolute, but the dot says in this directory. The other option is you do full path. Where am I at? /home/jwade/s1.sh. That's full path. So you can do full path. You can do the ./s1.sh. Or, once again, you put it in your path, and I just showed you how, you can do a s1.sh. Those were the biggest things that I saw was, folks were having, and then eventually they figured out, oh, okay, I got to do the .1. Also, the script has to work. And if there's an if-then clause, make sure you do the multiple tests. Okay? Any questions on scripts? Any questions? Any questions? Answer no, or feel free to ask a question. Okay. Well, folks, that is it for class today. I'm sorry I ran a little over. Not too bad. Maybe 15 minutes over. Eventually, we won't run anything really kind of over. Or maybe we will. I don't know. So, But everybody have a wonderful weekend. I'll get this posted up as soon as I can. I'm going to stop recording here and